So, good morning everyone. You can say वैसे तो कौन है बोलो आप गुड मॉर्निंग एवरीवन मैं वेट किया हुआ है सभी ने वैसे
तो जी नमस्कार आइए
Morning to everybody.
ये बहुत खुशी की बात है आप भी देख रहे हैं सुन रहे हैं
नहीं, मैं कल भी सुनता रहा।
हाँ देखा मैंने
हाँ, मैं वो पुरानी कहावत कहता हूँ ना, काव्य शास्त्र विनोदेन
कालो गच्छति धीमतां व्यसनेन तु मूर्खाणां निद्रया कलहेन वा
And I'm just checking you can hear me okay?
Yeah, that's fine, absolutely fine.
And you can see my slide?
Yes, slides are clear, your voice is clear, the background is very
the second
amusing.
slide is you've seen the second slide?
Yeah, turn on sound. Yeah.
Okay, good.
Yeah, okay. So I'll just check with the president and then we'll start soon.
Sure.
यही प्रोत्साहित करेगा आज राम सुब्रमण्यम अध्यक्ष उसका सेशन का।
Testing.
नोट्स भी करते हैं ना।
गुप्ता जी, आपको माइक म्यूट करना है।
अच्छा,
हाँ हाँ, बस, वेरी गुड।
नमस्ते जी।
हाँ नमस्ते सईद, आइए।
क्या हाल है?
हाँ सब ठीक है।
बहुत
वेरी गुड।
शुक्रिया।
Dear friends, so I'm delighted to welcome you all for the third day of the ISHM conference that is being held via web. So today we have 5 speakers in the first session, and it will be commencing with a very interesting presentation by Jonathan Crabtree. This Jonathan Crabtree has been deeply interested in knowing the development of Indian mathematics right from his school days. And he has been intrigued about zero, and I have had occasions to listen to a couple of talks in the web wherein he has been passionately arguing. So the contributions of India need to be recognized, particularly has been touching upon Brahmagupta. So once I remember himself writing to me about the verses of Brahmagupta, and I remember sharing with him the verses in Brahmagupta's Brahmasputa Siddhanta. Ever curious and addicted to discovery of zero, Jonathan began exploring the history of mathematics in 1983. He was born in 1968, which means at the age of 15, he started exploring seriously. As an elementary maths historian and podometric creator, Jonathan is a guest lecturer at schools, universities, and conferences. His provocative presentations reveal how the foundations of Bharatiya mathematics are often superior to Western ideas taught today. So this is, in short, an introduction to Jonathan Crabtree. I invite Jonathan to start his presentation.
Thank you very much for your introduction, Professor Ram. As you can see, I've titled my talk Notes. This is not my paper that I would like to submit to the Society. These are just some slides that indicate the flavor of what my upcoming paper will be. So this is Notes on Brahmagupta's definition of zero failing to be transmitted to Europe via the Western world. So for this talk, I'm just going to request that all participants can mute their microphones, but turn on the sound, and don't ask any questions unless I ask you to. So I've got a lot of material to get through. I'm probably not going to get through as much as I would like. But anyway, let's get on. So I'm going to define elementary maths foundations as concerning counts, measures, and relationships between quantities that reveal predictable patterns. So I'm starting off with a definition of number as numbers counting and measuring quantity, and also counts of absolute value, binary operations. So you're familiar with Brahmagupta's 7th century sign laws, as we just heard in the introduction, for positives, negatives, and zero. And there we have perhaps the best critical edition, which I have made a digital copy of this 1902 edition of the Brahmasputa Siddhanta. If anyone wants a copy, it's available on my website. Here we've got from chapter 18 verses 30 to 35, where I've analysed with the help of several Sanskritists, Dr. Avinash Ram, you, Clemency Montel, Agatha Keller, many people have helped me navigate into the Sanskrit, and I've been able to then perhaps bring it to light based on my interpretation of mathematics from other cultures as well. So from chapter 18 on algebra, in my interpretation, 18 simple sutras of symmetry emerge that agree with basic laws of physics, plus, as Avinash would also have us know, a contentious concept for division by zero. So here we have Brahmagupta's 5 addition sutras or laws. We've got the Sanskrit up the top, and we've got the very simple laws of sign for addition involving positives, negatives, and zero. Nothing surprising yet. Here we've got the subtraction sutras as well. And what we start to notice is divergence from Western teachings on mathematics. And I'll get into that maybe a little later on. Here we've got the multiplication sutras, and then also the division sutras as well. So altogether, I've got 18 of these laws that I have been able to teach very young children how they all work. So despite this symmetric zero-based genesis, a brief cross-cultural review reveals an incomplete understanding of Bharat's zero in the medieval Arabic world. So it appears that zero as a placeholder was transmitted via the Arabic world to Renaissance Europe, yet the role of zero as a number defined by Brahmagupta as the sum of equal yet opposing positive and negative quantities was not. It was neither grasped in the Middle East nor transmitted to Europe. So here we've got a map, and I'll throw myself in the middle just there. We've got, in the year 628, we've got Brahmagupta's definition of zero as the sum of equal and opposite quantities. And then it travels over to Al-Khwarizmi in the 9th century in Baghdad. And from there off to Northern Africa, it goes to Fibonacci, and then eventually to Robert Record in England. So we see Robert Record here, and I've made this obviously into a fun cartoon. Brahmagupta, I wasn't told about your zero definition or your 18 sutras of zero, positives, and negatives. So what I'm saying is that the travel from East to the Middle East to the West was all about the zero placeholder, and there was never any acceptance of zero as a number of the same status of the other the numbers, and there was an absence of an understanding of negative quantities being equal and opposite. What the West came to be teaching everyone is that negatives by definition are less than positives. So neither zero nor the negatives appear involved in the development of Arabic algebra. So these sutras or rules are correct with 21st century maths pedagogies, yet they remain disconnected from post-Vedic Bharatiya maths. So the sutras are correct, and yet and they're correct in terms of the laws of physics, but our pedagogies are not connected. So this talk reveals meta-mathematical disconnects and how they imperceptibly arose during the passage of time and place. And just here I've got a tweet which I put up a while ago. I don't understand Sanskrit. I've had to explore in many different languages, but I also wanted to again publicly thank two of the people who've been involved with this conference. And as I mentioned before, I've had lots of other help as well from professors around the world. As you can see here, when I've been analysing what I've needed to explore in elementary foundations of mathematics, I've had to explore in many languages: Greek, Arabic, Latin, Sanskrit, Swedish, Czech, Chinese, Mandarin, Hebrew, and so on. I do not speak these languages, but what I've had is expert help translating all of these diverse languages. These examples here are of Euclid's definition of multiplication. And that was the problem that I noticed when I was in class 2 at the age of 7. I disagreed with my teacher, and I had picked up a major problem in the foundations of mathematical logic. So, but first, some ballet. I want you to, in fact, this is not going to work actually. I'm going to have to just zip through these slides. What we've got is, we've got some images here that I've just forgot. I've got this on Zoom, and it's not actually able to show video. But if I survey people about which way is this ballerina circling, going round and round and round, around about 60% of people say that she's going clockwise, and about 40% of people say that she's going anti-clockwise, even though everyone is looking at the same image. If you go onto my Twitter page at the moment, at @jcrabtree, you'll see this video actually working. So sorry, this is just a bug in Zoom that it doesn't do animated video yet. So anyway, she spins both ways, and here are the two images, exactly the same image, but our brain picks up different spin rotations. So like mathematics, this dancer is spinning both ways based on our perception. So the mathematics that we've had passed on to us over millennia are biased towards the right-hand side of the number line and biased towards what we consider positive quantities, and yet what's positive and what's negative is completely arbitrary. So if we complete the phrase, and you might be able to do that, for every action there is an, you're familiar with the answer, I'm sure. For every action there's an equal and opposite reaction. So what we're starting to see in the laws of physics is when we assign numbers to the only things that are in the universe, which is matter and energy, numbers can only represent positive quantities of energy and positive quantities of matter. And so we start to see that there's a symmetry in physics disconnected from integer ordering logic and much else. So if I give you an example here, we've got one negative electron and one positive positron. They sum to 0. They cancel out each other out, they annihilate each other, release a little bit of energy in the form of a photon, but we have one negatively charged particle, one positively charged, and they sum to 0. And we don't say that a negative electron by definition has to be less than a positive positron, but that's what our elementary mathematics education would have us believe, which is not how the universe works. So symmetry is when things are the same around an axis. So seeing symmetry and discerning when it breaks is a key for understanding both mathematics and physics. So if we consider the Big Bang for a moment, it's almost as if Shunya was decompressed, creating infinite magnitudes and multitudes from 0. And if we consider some of the aspects of physics, we've got the zero-sum universe. We've got the conservation of matter and energy, and we've got Newton's third law. And all of these aspects go into Brahmagupta Bhaskara symmetry, and podometic. So what I'm doing is I'm building a system of mathematics to replace arithmetic. That's what I set out to do in 1983. I decided to fix mathematical foundations and create my own mathematics. So if you search on podometic, you'll probably see lots of things online. But my goal is that the new curriculum of podometic Bhartiya mathematics might one day start to slowly get into the Indian foundational curriculum from Anganwadi up to class 5 at least. And even if children in class 1 get a grasp of these, from class 1, children will start to understand positives and negatives intuitively and very simply. So if we've got planet negatron and we've got planet positron and we've got a body in the middle, what we have again is the two opposing forces sum to 0 gravity if we're in between those two planets. So whenever opposing quantities of forces or directions are equal, you're going to find 0. But this sense of symmetry of force and matter never came through ancient Greek geometry. And I'm going to move on to that shortly. So here we've got the elements of a basic number line with a happy smiley little 0 in the middle. And here I've coined a phrase I call the 0 point choice. So here we've got some artwork, famous artwork from Escher. And what I've done is I've put on a couple of rulers into the hands, not exactly straight edges because there are some markings on them. But what we have when we consider construction of geometric diagrams and also proofs is we have to make a choice from the first point that is drawn, and I call it a 0 point because, as you know, in Greek mathematics, a point has no magnitude in any of its 3 dimensions. So it is effectively, in Greek geometry, a local 0. So we've got the 0 point choice, and that means that whenever we draw a point for the construction of our geometry, we have to, from that point, decide which direction do we go. And it's an arbitrary choice. And we see through the history of mathematics that there've been many arbitrary choices that became laws and rules, very dogmatic approach. So what we then can do is revisit proportion, and proportion is the key that unlocks the language of the universe, and it also unlocks our mathematics as well. So if I ask you whose handwriting is this, you might recognize the Latin. You may not recognize the handwriting, but that's the handwriting of Isaac Newton. And that's the copy of his famous Principia that I have held in my hands and turned the pages. And it's quite an awe-inspiring thing to be able to handle books that are, in this case, from the late 17th century. In this case here, I've just zoomed in a little bit, so you can see there's Isaac Newton's own handwriting in the margin, and this is a first edition Principia, and he's making notes for his second edition. So whose geometry is this? That's my finger, and this is the first printed Euclid's Elements, and I'm pointing to the Latin and investigating all the different translations that have been done over the centuries in many different languages to see where the logic, the translations broke, because we've had breakages in translations that haven't really been discussed. So there's my finger pointing to the definition of multiplication. So now I'm going to move on to Al-Khwarizmi's equation types to start to demonstrate how Barat's zero did not get understood in the Middle East. So we've got here, now I'm just going to say, because I'll be corrected if I don't say this, Arabic algebra entailed steps to arrive at co-equal polynomials as we know them. So the following is an anachronistic styling as modern equations. So of course, Robert Record gave us the equal sign. Al-Khwarizmi didn't have them. So we've got equation types such as ax squared equals bx and ax squared equals c. And what I have done for having a bit of fun is Al-Khwarizmi talked about balancing equations, and the Arabs were great traders. So I've, in my own mind, had a balancing metaphor of using balance pans. And so we can see that ax squared balances, it confronts bx, and ax squared confronts or balances c in these equation types. And there are more equation types that Al-Khwarizmi had. Bx equals c, ax squared plus bx equals c. But what we notice missing is we don't have negative quantities appearing on their own. So nowhere in Al-Khwarizmi's or Arabic algebra, for that matter, do we find equations such as ax squared minus bx equals negative c. And in the balancing pan metaphor, you can understand how could you have positive quantities on the left balancing with something that's, in our own interpretation, less than zero. It doesn't make any sense, and it didn't arise in the Arabic algebra. And also, what we also know is that ax squared plus bx plus c balancing to zero also didn't emerge out of the Middle Eastern approach to algebra. And yet we know that from Brahmagupta, he gave us those laws of sign in his chapter on algebra. And so whilst negatives and zero were incredibly well documented in Barat's algebra, there's no evidence of it being transmitted to the people who then passed on Hindu mathematics to the West. So negative terms did not occur in Arabic algebra, yet today you wouldn't know that. You wouldn't know that today. So if we have a look at Al-Khwarizmi's algebra text, circa 820, and I also just want to correct a misunderstanding. People assume that Al-Khwarizmi wrote his book on Hindu reckoning, Hindu arithmetic first, and then followed up with his algebra. But that's actually not what happened. He wrote his algebra text first, and then about 5 or so years after that, that's when he wrote his arithmetic text. And we know that because he refers to his algebra in his arithmetic text. So this is, I'm not going to pronounce it, but we've got the Arabic, we've got the translation of sorts, but we see the phrase al-jabr in the title, and al-jabr, as you know, morphs into the word algebra today. So we know that this title becomes something like the compendious book on calculation by completion or restoration and balancing.
So I'm sorry, you just have 5 minutes.
Okay, all right. In mathematical language, the verb jabra means to transpose negative quantities to the opposite side by changing signs. But and I've just got many examples of this where lots of different commentators keep talking using negative terms, but what's happening is there are no negative terms in Arabic algebra. All they are positive terms being subtracted. So if we go back to the addition sutras, what was documented in India, only one would have been understood in the Middle East, because all the other 4 sutras were referring to zeros and negative terms, and that's not what was understood in the Arabic world. So here we've got all of the sutras, and this is the one that's the most important that needs to be reworked into modern curriculums. Addition Sutra 4, when positive and negative are equal, the sum is 0. So there we've got a 0. We've got, and there's another 0. We've got 2 positives and we've got 2 negatives, and that is a definition, a quantitative visual definition of 0. So if we take away the 2 positives from 0, you can see with your eyes that you're left with 2 negatives. If again from 0, we take away 2 negatives, we see with our eyes that we're left with 2 positives. So we can start to see very simple visual instantiations of Brahmagupta's sutras, and they go all the way through multiplication and division as well, with fun games for children in class 1, 2, and 3. So we can add integers to 0, and that's what I've got here with a reworked number line in which we have symmetry restored. So we have positives on the right, we have negatives on the left. What we can then do is we can also subtract integers from 0, and then we have this sort of concept, which again is pure symmetry, and from this we can then develop what's called a Brahmaguptan plane. So as I'm short on time, I don't have the opportunity to explain how it works, but essentially we pull apart the operations of arithmetic and separate out the quantities as the multiplicands and the multipliers as the abstracted numbers. And we start to then have a very simple model where children can understand what's going on with multiplication across all 4 quadrants of what we know as the Cartesian plane. I do have a paper all about the Brahmaguptan plane, where I go into great detail about and also discuss how we could have developed geometry out of negative and positive areas as well. And we can do that dating back to Egyptian geometry. So what we need to do is to bring in negative line segments. We need to have in negative areas and negative volumes. And all of these things become very intuitive for children when we correct the foundations that were broken, typically in Europe. So I'm going to just whiz through these. I'll make available this PowerPoint presentation to people who choose it. But here we can see the Brahmaguptan plane in the 4 quadrants. And it's a very prescriptive, very simple concept. We're in quadrant 1. We've got 8 positives added 3 times to 0. In quadrant 2, we've got 10 negatives added 5 times to 0. And that's what was missing. In the West, they never had the accumulation or the subtraction from 0 in their definitions of the algorithms. So Euclid didn't have 0 or 1 as number. And therefore, believe it or not, the identity elements of 0 and 1 were then missed from definitions of algorithms in Europe, as crazy as that may seem. So we've got some things which work with Western mathematics, and we can give it a thumbs up. But we also have some things which do not work and break the laws of physics. So just very quickly here, Brahmagupta says that when a smaller is subtracted from a larger, the sign stays the same. And so with 8 negatives minus 5 negatives, the 5 negatives are smaller than 8 negatives, and that's why the sign stays the same. And we have 3 negatives as the answer. And yet the West would say that -5 is greater than -8, which is not correct logic. So again, Brahmagupta says that when a larger is subtracted from a smaller, the sign will change. And so we see that with -3 minus -7, the sign changes and the answer becomes +4. So -7 is actually larger than -3, according to the laws of physics, according to Brahmagupta, and according to common sense. A debt of 7 rupees is greater than a debt of 3 rupees. So we've got the actual quotes from the people in the Middle East, with Al-Khwarizmi talking about, I had seen that the Indians had set up 9 symbols in their universal system of numbering, and every number is put together above 1. So Al-Khwarizmi doesn't mention 0, and also he doesn't even accept the number 1 in the set of numbers. We go from him, we go to Al-Euclidisi, and again he mentions 0, but Al-Euclidisi, the Euclidist, only mentions 0's role as a placeholder. And again, we see a very strong Euclidean influence in this time in the Middle East, which prevented the proper understanding of 0. Now we can then go on to other Arabic writers as well, and none of them really put 0 up there in the realm of number. And on it goes. So what we can do is we can say that with the birth of the Cartesian plane, 1,000 years after Brahmagupta, we look at the original diagram from La Géométrie, and this is what led to the Cartesian plane. But we don't have, and there's nothing overly new here. This is Euclid from book 6, I think proposition 13 or so. But we've got line segments, and this is for the model of multiplication. So what we can then do is put this into a GeoGebra applet, and we can then use similar triangles to work out the products of multiplication. This was the good idea that got us off the area model. And so we've got a blue multiplicand, we've got a green multiplier, and we've got a red product. So if we...
I'm sorry, Jonathan. So you may have
Yes?
you may have to wind up, please.
Okay, I'll just show you one more picture.
Yeah.
And that is that when we have the concept of negative magnitudes, which is very much an Indian concept with 0 mediating left and right, positive and negative, we have a geometric model for negative magnitudes, a negative multiplicand and a negative multiplier producing a positive product. So we can go back and revisit all of Euclid's work, all of Descartes' work, and lots of algebra with the concepts from ancient Bharat, and then suddenly a whole lot of simpler mathematics starts to emerge. So thank you very much for watching.
Can I ask a question, Professor Ramswamy?
Yeah, yes, please.
Thank you, Professor Captri. You have very beautifully sort of told us how negatives and 0, the physicality of them was completely missed in their transmission to West Asia and to Europe. But I'm sure this continued in Indian mathematics. Brahmagupta pioneered, and there were so many Indian mathematicians. So have you seen anything in them where this physicality, how it sort of reflects? I know that Bhaskara says Ranatvam, Vyatyayena, Vyatirekena, and all that, the kind of idea you are saying. But how does it in pedagogy, etc.? There are so many beautiful textbooks written in India. They must have used the Brahmagupta method.
Look, I would say that there hasn't been a whole lot of proportion work across positive and negative that I've come across from the Indian writers. We do have Krishna, who very much speaks about if, for example, East is positive, then West is negative, and that's in the 16th century. But really the problem came with the writings of John Wallace in 1685, who created a number line where going backwards instead of retreating, and where advancing is positive and retreating is negative. If you are forced to go backwards, John Wallace said that we've advanced less than nothing. And that introduced the absurd idea of negative magnitudes being less than zero. The main problem is that the writings of Aryabhata and Brahmagupta and Bhaskara weren't translated into English until the 19th century, around about 1816, 1817, with people like Taylor and Colebrook and so on. So the pedagogies in the West had been well and truly locked in. And remember, you also had the Macaulay education policy, where all of the wonderful opportunities to teach in Indian mathematics in the last couple of 100 years were wiped out by teaching a British mathematics curriculum. So look, I haven't seen a whole lot of basic mathematics texts that go into the operations and the simple geometry of positive and negative. I would love to find it. I haven't found it yet. So here's hoping that maybe with my making new friends with the society, we might be able to explore this further.
Thank you.
Can I make a comment?
Very quick, please.
Yes.
So we have
Yes.
to move further. Yeah, the last.
Yes, thank you for your nice talk. In this conference, I presented a paper of the Al-Kandi. If you want, I can show the paper, manuscript like that. In that manuscript, Al-Kandi for cryptography used 0 for the first alphabet number. That means changing A to Aleph or A to 0. I think in the 5th century, the Al-Kandi knowing about the 0 for cryptography is. If you are interested, I can send the paper for you, or I can show here.
Yes, I'd be very interested in that. And look, I'm very, very curious about everything that involves the foundations of maths up to algebra. I don't really go into trigonometry and calculus because I really wanted to get the elementary mathematics foundations realigned with the laws of physics. And we just see that the Indians were astronomers, so they were empirical observers, and their numbers had to match their science. And unfortunately, the West got their maths from the philosophy of Aristotle that led to what could be done with geometry. And really, it was an esoteric art that had laws and rules that had to be enforced in the face of the logical foundations that both China and India had.
Okay.
I have 6,000 manuscript. If you are interested, I can introduce to you.
Yeah. Okay. I think we may have to close this talk session. We thank the speaker for presenting a very interesting talk, which invited a lot of attention from various audience. So with this, I invite the second speaker of the morning session. So the second speaker is Dr. Keshav Milnad. So he completed his PhD at IIT Bombay. He initially got trained in a Gurukula system in Bengaluru. So having studied Veda, Shastra, Yoga, and so on, so he also got interested in science, and he did his PhD at IIT Bombay. And currently, he is working as a postdoctoral fellow at IIT Gandhinagar. So he is working on Indian mathematical and astronomical texts. So he'll be presenting his research work. I invite Dr. Keshav Milnad. Yes, please.
Sarvebhya Suprabhatam. Good morning to all. Thank you very much, Acharya, for your kind introduction. I'll share my slide quickly.
Yes, please.
Is it visible?
Absolutely fine. Go ahead.
Okay. So today I'll be talking upon the rationale behind the corrections applied to the solar longitude in the Indian tradition. So this will be the outline of my talk. First, a brief introduction, then concept of Abdapa, that is Lord of the Year, then concept of Avadhi, true solar longitudes given in the Jagat Bhushana, and the 4 corrections, Deshantara, Udayantara, Bhujantara, and Chara. Then how do we apply these corrections? Then what are the true longitudes of the sun after the correction? So as we know, the Panchangas or the almanacs have a great importance in our day-to-day life. In ancient times, it was for rituals and customs and also agriculture and navigation, etc. But nowadays we have more usefulness of these Panchangas and almanacs. Since ancient times, finding the accurate positions of the planets was utmost important. And gradually, when we see tantras and karanas, the computations which involved very large numbers in Siddhantic period, they were simplified. And when we travel to the tabular texts, so where we have a text which gives the procedure or the rules to compute the tables and use the tables for different locations, and to use them to minimize the tedious work in the computation of the Panchangas. And what is the general procedure to compute a planetary position? So first we have the epochal positions. It can be at the beginning of Kalpa or the beginning of Kali Yuga or any given epoch. And then we find the mean longitudes of the planets. So that is straightforward. We get it from Hargana, that is number of days elapsed since the epoch and the desired date. Then we have to multiply this day collection or the number of days with the mean velocity of the planet. Then we find the mean longitudes. Then we have to apply 2 corrections. So that is Manda correction, that is Manda Samskara, and Shikhara correction. When we take the sun and the moon into consideration, we only apply Manda Samskara. And for other planets, we apply Shikhara Samskara to convert their heliocentric positions to geocentric positions. I will not go much into detail there. So my focus of this talk will be the corrections that we apply to get the accurate values of the longitudes. So before that, we need to understand 2 concepts, or we can say parameters or variables, which are relevant in this calculation. So first of all, it is Abdapa, that is Lord of the Year. So what is this? We know that the sidereal year was this 365 and so and so. Then it was corrected by Bhojaraja in his Raja Mriganka after incorporating the Bija corrections. Then the corrected length of a sidereal year is this, as you can see. So we employ a very unique term here. It's called Avadhi. It is a technical term. So where we divide the sidereal year into 27 parts, where the first 26 parts are of 14-day intervals. Okay, then we find this 364 days plus 1 day and a quarter. So this is a very interesting term, because this is useful in different different calculations. When we want to find the weekday of a year, then we use the integral part, and where when we want the instant of Mesha Sankranti, we take the fractional part. So as we know, this is a multiple of 7. So again, 364 is multiple of 7. So we eliminate all the weeks in a year, except for this 1 day and a quarter. So this will give you the exact instant of Mesha Sankranti of the next year. So here, this particular number is called Abdapa, Lord of the Year. Why it is Lord of the Year? Because the weekday of the year will be the integral part, and this will determine the weekday of the year. In Jagat Bhushana, so which is written by Haridatta, and the epoch is 1560 Shaka or 1638 Common Era CE. So here he gives cyclic periods for different parameters like Abdapa, like Shuddhi, Epact, so on and so forth. Also for the planets, because in those many cycles or cyclic in that cyclic period, the planet in question will make integral revolutions and will leave only a very small residual. And to incorporate that residual, he also gives the corrections. So when we take 89 as a cyclic period of Lord of the Year, and we multiply with this yearly increment, then after 89 years, this is a very small residual left when we take mod of 7. Then how to incorporate this? Then in another verse, he gives the correction. Gadani chakrani bhajet vivedaihi ashtendrakaihi abdapa kendra yoscha, so and so forth. So we have to divide 1 by 42. So whatever is the quotient will be equal to the correction here. So here he gives, he tabulates all the Abdapa values for 89 years. So that we can see here, this is the epochal value, that is 1560 Shaka until 88, that is total 89 entries. So these are the values of Abdapa. Avadhi we have seen. Now, so why this division of Avadhi? Because when we have larger cyclic periods, it will be very tedious to give the computed values of the longitudes of planets and including sun and moon. This will be very tedious. So he divides them into 27 avadhis, and he only provides 2 longitudes for those 27 entries. So here we can see these are the avadhi numbers, and this is the true longitude of the sun. But this is for the mean sunrise at Ujjain, where the prime meridian passes. And this is the velocity, true velocity. So as we can see, it starts from 58 minutes, so on and so forth. And this is the difference between 2 entries. Now, to find the true longitude at true sunrise, we need to apply some corrections. So what are those corrections? Deshantaram phalam yatam charam bhuja phalam tatha varisheshanadhyam somranam kartavyam avadhos phutam. So he names these 4 corrections: Deshantara, Yata phala, which is also called Udayantara, and Bhuja phala, which is called Bhujantara in some texts, and then Chara. So these have to be applied positively or negatively to the nadis of the Lord of the Year. So here he's telling that we should apply to the nadis, that is a fractional part of the Lord of the Year, to get the accurate Mesha Sankranti instead of Mesha Sankranti. But we have to also apply these corrections for each avadhi entry. For each avadhi entry. Then we'll find the true sun, because this is solar table, true sun for true sunrise at the beginning of these avadhis. So he gives the correction. He computes them and gives the corrections. So these are the 27 avadhis: Deshantara, Yataphala, Chara, and Bhujaphala. So we have to see that Deshantara table is left blank because he computed all these values for the longitude of Ujjain. So there is no Deshantara. I will talk about Deshantara later, but Deshantara correction is nil at Ujjain's longitude, so it is left blank. Whereas he gives other corrections, then he gives the Trayakyam, that is the the sum of all these three corrections. So we can see Trayakyam here. So these are tabulated. So now let's see each correction one by one. So this is a this is the this is Earth and equator is here, and this is prime meridian passing through Ujjain, and this prime meridian intersects at Lanka at the equator, and we have two locations. One is to the east, and this Y is to the west. So Deshantara correction has to be subtracted when the observer is to the east. It has to be added when the observer is to the west. So we'll see that here. So in modern notation, this Deshantara correction is called time difference correction. So let T denote the longitudinal displacement between local meridian and prime meridian. Just a second. Okay, so here we see 4,800 is the circumference of the Earth at equator measured in yojanas, and in these many yojanas, sun travels, or any planet travels 3,600 vinadis, that is 60 times 60 ghatis, and times 60 we get vinadis per day. So if d is the distance in yojanas, then with the simple Trayarashika, that is rule of 3, we will find the time taken by a planet to travel in this small portion. Now we have to find out that in this time period how much a planet, it can be sun or any other planet, is going to travel given its daily motion. So for that we are going to use the daily motion of a planet. So when it is given in minutes, so we convert minutes, V is the daily motion of a planet, we convert it into degrees and multiply with this time period, then we get Deshantara correction. And as we have seen from the figure, it has to be added to the observer to the west, and it has to be subtracted to the observer to the east. Then the second correction is Bhujantara correction. So this is equation of time due to eccentricity. We know that equation of center, which is Manda Samskara. So it has two components. One is equation of time due to eccentricity and equation of time due to obliquity. So when the equation of center E is sine inverse of 14 by 360 times sine of this mean longitude and the Kendra. It can be of sun or any other planet. Then we find equation of center. So now we have to see that in given the daily motion of a planet, what is the change in equation of center. Then we find equation of time due to eccentricity, because this is Bhujantara correction. So how do we apply it? This is applied negatively when the true sun rises before the mean sun, and is applied positively when the true sun rises after the mean sun. I will not go much into detail. So here I have taken these values from Jagat Bhushana, and using this equation, I computed them. Then we find that more or less it is accurate. So why I did this? Because in Jagat Bhushana, he doesn't mention the formula that he has employed to arrive at these values. So an attempt has been made to verify the values. Somewhere we found that some scribal errors. So to rectify all those scribal errors, we need to recompute them using the formulas given in the earlier texts. The next correction is Udayantara correction. Here, as we have seen, equation of center, equation of time has two components, and this is the second component, equation of time due to obliquity. The interesting thing related to this Udayantara correction is that it was not mentioned in the earlier Siddhantic texts, but Shripadi first introduces this text, this correction, and then later Bhaskaracharya in Siddhanta Shiromani, he mentions this correction, Udayantara correction. So we find one approximated formula to calculate Udayantara, that is R sine of 2 times Sayana, that is precision corrected sun, divided by 5. So when we compute the values and compare with those given in the Jagat Bhushana, we find that the values given in Jagat Bhushana are accurate. And the next correction is Chara correction. So we know that ascensional difference, there is a small difference in right ascensions. Because of change in latitude, we find different ascensional differences. So when we have this ascensional difference, we have to take this, we have to convert this, the arc. I will show this in this figure. So this is the horizon, and this is a 6 o'clock circle, and the equator and diurnal path. So from equator to zenith, we have the latitude. So when we have latitude, then we find that this arc denoted by E and S prime, will be Chara correction, Chara, that is delta alpha. So because when the sun is in the northern hemisphere, it takes more, the daylight will be more. When the diurnal path or the sun is in the southern horizon, the daylight will be less. That is because of Chara. So this is the arc. So we can see that this Chara correction is applied negatively when in the northern declination and applied positively in the southern declination. And these are the computed values and the values given in the Jagat Bhushana. So we can see more or less very accurate. Then what we have to do? So he says that the Trayekya has to be applied. So in case of Ujjain's longitude, we only have three corrections. That's why we have Trayekyam. We have to add Bhujantara, Udayantara, and Chara. So if we denote Bhujantara by B, Udayantara by U, and Chara by C, then the true longitude of the sun will be mean longitude plus all these corrections. Sorry, there is a mistake. It is not mean longitude. It is true longitude at mean sunrise. True longitude at mean sunrise plus these corrections. We find the true longitude corrected. And then if it is other longitude, I mean, if Deshandara correction is valid for other longitudes, then we have to add all these three plus Deshandara. It becomes Chadushtayekyam. So these are the avadhis and the true sun at the beginning of these avadhis, and we have the Trayekyam given in Jagat Bhushana. And when we convert it into degrees, because we have to add it to the longitude of the sun, so we convert it into degree. So there are some different calculations we have to employ. Then corrected true sum will be this at the beginning of 27 avadhis, and this is the difference. So when we plot this difference, we find some more or less a sinusoidal function. This is not perfectly sinusoidal because of some approximations employed during the whole process. So this will be the end of my talk, and if there is any question, I'll be more than happy. Thank you so much.
Oh, thank you, Keshav. So now the floor is open for questions, if any of you have. I have a question now. So why do you use the word velocity? So that has a very specific connotation in physics. So you represent 58 and so on. So that seems to be the daily motion, right?
Yeah, daily motion. I meant daily motion only.
So it may not be very appropriate to use the term velocity because it has a very specific connotation.
Okay. But I have seen this this usage in many texts, so I thought.
So that may not be quite correct. Okay.
Okay.
And there was another term like Ashtendra Kaihi. What does it mean?
Ashtendra Kaihi. So we have 8, and Indra is 14. So it becomes 148.
So the number, was it corresponding to that?
So actually, it's a continuation. The first term, that is, yeah. So for Abdapa, we have 1 divided by 42, that is Dvivedaihi, and Ashtendra Kaihi is for the anomaly, lunar anomaly.
Okay. Okay. So if there are no further questions, we thank the speaker for his interesting presentation on Haridatta's Jagad Bhushana. Okay, thank you very much.
Thank you.
So we now move on to the third talk. The third talk is going to be presented by Dr. Sundari Kameshwari. Sundari Kameshwari is an assistant professor in IMS Engineering College, Ghaziabad. So what is your area, madam?
Sir, algebra.
Algebra, okay. So she has been continuously teaching for the past 17 years and has a PhD from Osmania University and has quite a lot of publications. So I request you to proceed with your talk.
Thank you, sir. Sir, are you able to see the screen, sir?
Yes, yes, yes.
Thank you, sir.
Your voice is clear, screen is also quite clear.
Thank you, sir.
If you can make it full screen mode, it may be better. Otherwise, also it's fine.
Okay. Except 1 second, sir. Is that okay, sir?
Fine.
Oh, I'll put in a slideshow mode. Okay, sir. Okay, this is Dr. Sundari Kameshwari. I'm an assistant professor in IMS Engineering College. I'm going to present a talk on Nilakantha's explanation of planetary motion in 15th century. This is my abstract. So this is only a talk. This talk is devoted to throw light on Tantra Sangraha of Nilakantha Somayaji. Nilakantha Somayaji was an adorable mathematician and an astronomer of 15th century, belonged to Kerala. His work was mostly in Sanskrit and also in Malayalam. There were several attempts made to translate and explain in detail all his works, in particular Tantra Sangraha. Tantra Sangraha is a book on astronomy, consists of 432 Sanskrit verses and 8 chapters. The first chapter leads with longitude motion of celestial objects. This talk is to study his theory on planetary motion in detail. This talk is divided into two sections. The first part of the talk is to study the biography of Nilakanta Somayaji, and second part is to throw light on the first chapter of Tantra Sangraha. The second part of this talk describes how Nilakanta Somayaji had described the division of time into smaller units. Suklapaksha, Krishnapaksha, Tithis, etc. Part 1 is the biography of Nilakanta Somayaji. Kelalur Nilakanta Somayaji was born to a Nambuduri Brahmin family which came from South Malabar in Kerala. The Nambuduri is the main caste of Kerala. It is an orthodox caste whose members consider themselves as descendants of the ancient Vedic religion. He was also referred to as Kelalur Komatiri. Nilakanta was a major mathematician and astronomer of Kerala School of Astronomy and Mathematics. He was born on Kali Day, Wednesday, June 14, 1444, and was a resident of Trikantiyur near Tirur, Ponnai Taluk, South Malabar, recorded in Siddhanta Darpana of his works. His teachers were Ravi, with whom he studied Vedanta, and Damodara, son of Parameswara, who initiated him into astronomy and the underlying mathematical principles. He worshipped the personified deity Soma, who was the master of plants and the healer of disease. This explains the name Somayaji, which means he was from a family qualified to conduct the Soma sacrificial rituals. Nilakanta lived up to a ripe old age, even to become a centenarian, and is attested by contemporary reference made to him in Malayalam work on astrology, Prasnasara, composed in 1542-43. In Aryabhatiya Bhashya, Nilakanta Somayaji has stated that he was a son of Jatavedas, and he had a brother named Sankara. Somayaji has further stated that he was a Bhatta belonging to Gargya Gotra and was a follower of Asvalayana Sutra of Rigveda, which was a manual of sacrificial ceremonies in Rigveda. His wife was named Arya, and he had two sons, Rama and Dakshinamurti. References in his own Laghu Ramayana made by Rama indicate that Nilakanta Somayaji was a member of the Kelalur family, Sanskritized as Kerala Sadgrama, residing at Kundagrama, now known as Trikantiyur in modern Tirur, Kerala. He is considered an equal to Vatesari Parameswara Nambuduri, who did a major work on astronomy through observations. Nilakanta writings substantiate his knowledge of several branches of Indian philosophy and culture. It is said that he could refer to a Mimamsa. Mimamsa is a Hindi Sanskrit word meaning reflection or reward thought. It is one of the 6 darshans or ways of viewing the world. The other 5 darshans are Yoga, Samkhya, Vaisheshika, Nyaya, and Vedanta. He used Mimamsa as an authority to establish his viewpoint in a debate. One of his most influential works was the comprehensive astronomical treatise Tantra Sangraha. The Tantra Sangraha is very important in terms of mathematics which Nilakanta uses. In particular, he uses results discovered by Madhava, and it is an important source of remarkable mathematical results which he discovered. However, Nilakanta does not just use Madhava's results, he extends them and improves them. An anonymous commentary entitled Tantrasangraha Vakya appeared somewhat later in 1550. Jeshtadeva published commentary entitled Yukti Bhasha that contains proofs of earlier results by Madhava and Nilakanta. In his Tantra Sangraha, Nilakanta revised Aryabhata's model for the planets Mercury and Venus. His equation of the center for these planets remained the most accurate until the time of Johannes Kepler in the 17th century. In his Aryabhatiya Bhashya, a commentary on Aryabhatas, Nilakanta developed computational system for a partially heliocentric planetary model in which Mercury, Venus, Mars, Jupiter and Saturn orbit the Sun, which in turn orbits the Earth. Similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. Most astronomers of the Kerala school who followed him accepted his planetary model. He had also composed an elaborate commentary on Aryabhatiya called Aryabhatiya Bhashya. In this Bhashya, Nilakanta had discussed infinite series expansions of trigonometric functions and problems of algebra and spherical geometry. Graha Pariksha Krama is a manual on making observations in astronomy based on instruments of time. Nilakanta's works. Tantra Sangraha is not the only work of Nilakanta he wrote. In all, he wrote about 10 treatises on astronomy. Golasara, description of basic astronomical elements and procedures, written 56 verses and shows how mathematical computations are used to calculate astronomical data. Siddhanta Dharpana is a short work in 31 slokas enunciating the astronomical constants with reference to the Kalpa and specifying his views on astronomical concepts and topics. Chandrachaya Ganita is a work in 32 verses on the methods for the calculation of time from the measurement of shadow of the gnomon cast by the moon's zenith distance, and vice versa. Aryabhatiya Bhashya is an elaborate commentary on Aryabhatiya, also discussed infinite series expansions of trigonometric functions and problems of algebra and spherical geometry. Siddhanta Darpana Vakya, commentary on his own Siddhanta Darpana. Chandrachaya Ganita Vakya is a commentary on his own Chandrachaya Ganita. Sundar Raja Prasnottara, Nilakanta's answers to questions posed by Sundar Raja, a Tamil Nadu-based astronomer. Grahanadi Grantha is a rationale of the necessity of correcting old astronomical constants by observations. Graha Pariksha Krama, description of the principles and methods for verifying astronomical computations by regular observations. Jyotir Mimamsa is an analysis of astronomy. Now let me discuss about Tantra Sangraha a little bit. It is based on the epicyclic and eccentric models of planetary motions. The first two chapters deals with the motions and longitudes of the planets. The first chapter is on the mean motion of the planets. Second chapter is on the true longitude of planets. The third chapter is a treatise on shadow, deals with various problems related with the sun's position on the celestial sphere, including the relationships of its expressions in three systems of coordinates, namely ecliptic, equatorial, and horizontal coordinates. Discusses on three questions relating to the diurnal rotation of the sun. The fourth and fifth chapters are treatises on lunar eclipse and solar eclipse. And these two chapters treat various aspects of the eclipses of the sun and moon. The sixth chapter is on Vyatipata and deals with the complete deviation of the longitudes of the sun and the moon. The seventh chapter is on visibility computation, discusses the rising and setting of the moons and planet. The final chapter on elevation of lunar cusp examines the size of the part of the moon which is illuminated by the sun and gives a graphical representation of it. Part 2 is on Neelakanta's explanation of planetary motion. So the reference I have taken from Tantra Sangraha of Neelakanta Somayaji by Professor Ramasubramanian and M.S. Sriram. I have taken officially permission from M.S. Sriram, Professor M.S. Sriram, to present the details. So I am asking the permission from Ramasubramanian sir also to present the talk. He Vishnu Nihitam Krishnam Jagat Tvayave Karini Jyotisham Jyotishe Tasmai Namo Narayanayate. Here, the author Neelakanta begins the work of Tantra Sangraha with an invocation to Lord Vishnu. The first quarter of the verse indicates the day on which Sri Neelakanta started his work. He Vishnu Nihitam Krishnam refers to a number 16,80,553, which corresponds to March 22nd, 1500 C. Here, the assumption is being taken that Kali Yuga has been started on 17 or 18, 3102 BCE. Sloka 2 of Tantra Sangraha. Here, he explains the measurement of civil and sidereal day. Rave Pratyak Brahmam Prahu Savanakya Dinam Nunam Aksa Mraksha Brahmam Tadvat Jyotisam Prerako Marut. Rave means Ravi, the sun. Pratyak means west. Brahmam means motion. Pratyak Brahmam means Pratyak westward motion. Sun takes one complete westward motion constitute Savadana civil day. Akshab Brahmam sidereal day is the time taken for one complete westward revolution taken by the stars. Jyotisham Prerako Marut. The impeller of celestial objects is Marut, the wind. In modern spherical astronomy, this apparent westward motion is termed as diurnal motion. This corresponds to the time interval between successive meridian transits of a particular star, which is the same as the time taken by the Earth to complete one rotation around its own axis. It is precisely this rotation of Earth which makes the stars appear to have diurnal motion. Apart from diurnal motion, which is westwards, the stars do not have any eastward motion of their own. However, this is not true of the sun, moon, and other planets. They have both diurnal motion and westward motion relative to the stellar background. It is said that Savana Dina, the civil day of humans, is the time taken by the sun for completing one westward revolution. Likewise, Aksa Dina, the sidereal day, is the time taken by the stars for one complete westward revolution. The impeller of the celestial objects is the Maruti wind called Pravaha. While explaining the role played by the Pravaha Marut, Yuktidipika describes how the eastward motion of the celestial objects in the background of stars can be inferred from the conjunction of these objects with different stars whose relative positions are fixed in the sky. Sloka 3 and 4. Brahmanam puryate tasya nadi shastya muhurmuhu. Vinadikapi shastyanso nadya gruvaksaram tataha. Prano gruvaksaranam shat dashakam chakraparyaye. Khaka shadgana tulyaste vayu samjhavo yataha. Brahmanam is a revolution of the stellar sphere, the earth. Puryate completes. Nadishacha 60 nadis. Muhur muhu again and again. Vinadi 1 upon 16 of nadi. Shatyamso nadya 1 upon 60 of vinadi. Gruvaksaram. Prano gruvaksaranam sashtya dasakam. 10 gruvaksaram is equal to 1 prana. Ghatika or nadi is equal to 1 upon 60 of a day, which constitute 24 minutes. Vinadi 1 upon 16 of nadi is equal to 24 seconds. Gruvaksara 1 upon 60 of vinadi is equal to 0.4 seconds. Prana 10 gruvaksara is equal to 4 seconds. It is interesting to note that the average time taken for a healthy person to inhale and exhale is equal to 4 seconds. In Vateswara, Siddhanta takes Truti as the smallest unit of time. 1 Truti is equal to 8.889 into 10 power minus 6 seconds. Slokas 5 to 8 describes about Indian calendar system. Pakshas and Chandramasas. Pakshas means fortnights. Chandramasa is a lunar month are defined. The system is based on motion of moon relative to the sun. The lunisolar nature of the Indian calendrical system is evident from the fact that some of the social, religious functions or festivals are celebrated according to tithis, nakshatras, etc. While others depend on Sankranti, Ayana, etc. are based on the motion of the sun alone. For instance, festivals like Ramanavami, Ganesh Chaturthi, etc. are based on moon's position relative to the sun, whereas others like Makara Sankranti, Visu, etc. are based on sun's position against the background of stars. Sloka 5. Purva Paksha Sashankasya Viprakarso Rave Samrataha Sannikarso Parapaksha Sita Vriddhi Kshayayu Yayoho Matastabhyam Mataschandraha Trimsatit Yatmakaha Purvapaksha fortnight period away from the sun. Aparapaksha other fortnight period towards from the sun. These two periods in which brightness of the moon increases and decreases constitute one lunar month is equal to 30 tithis. Suppose at a particular instant the sun is in conjunction with the moon. This instant is taken to be the ending moment of the Amavasya or the new moon day. As the moon's angular velocity is much greater than that of the sun, the angular separation between them keeps increasing. A tithi is the time unit during which the angular separation between the sun and the moon increases precisely by 12 degrees. A lunar month consists of 30 tithis and fortnights, the Shukla bright and Krishna dark. When it becomes exactly 12 degrees, that corresponds to the ending moment of first tithi, namely Pratipad, Pradama or Padimi. Similarly,
Sundari, you may have to just complete in 5 minutes.
Yes, sir.
Okay. Proceed.
Sir. Thank you, sir. Similarly, when the angular separation becomes exactly 24 degrees, it corresponds to the ending moment of second tithi, namely Dvitiya and so on. The names of different tithis constituting a lunar month are listed in the following table. Pratama, Tritiya, Tritiya, Chaturthi, Sabdiya. When the angular separation becomes exactly 180 degrees, the moon will be in opposition to the sun and it corresponds to the ending moment of Pura Paksha at the first half of the lunar month. The first fortnight consists of 15 tizis. It is also referred as Sukla Paksha or Sita Paksha, bright fortnight. The differences of calendar in north and south. The Amanta system is more popular in South India, whereas Purnimanta system is so in north. For instance, places like Tamil Nadu, Andhra Pradesh, Karnataka, we follow Amanta system, and places in north like Uttar Pradesh, Bihar, Rajasthan, they follow Purnimanta system. As a result, the commencement of lunar year also differs by 15 days. The commencement of Ugadi lunar year is celebrated fortnight earlier in the north. Thank you.
Are any questions? Okay, so if no questions are there, I just have a comment. So you may have to train yourself to read the verses.
Yes.
So more correctly. Okay.
But actually, I don't know anything about Sanskrit. Little about I studied in 11th and 12th.
Okay. How?
But I tried.
Yeah.
I was actually trying to read Tandra Sangraha, so I could come across some papers and also your book. Your book, that was very much explained in detail. So I took the book and I was studying your book only.
Okay.
This is by chance.
Yeah, very good. Anyway, so glad that you are interested in this, but if you can improve upon, that will be much better. Okay.
Yes.
So with that comment, I think we move on to the next speaker. Our next speaker is Udayaraj Patare. Yes. So Udayaraj Patare is assistant professor in the Department of Mathematics in Ahmednagar College, Ahmednagar, Maharashtra. So I invite Dr. Patare to present his talk.
Yes, sir. Thank you. Ma'am, please stop presenting so that I can present it. Yes. Is it visible, sir? Is it visible to all?
Yes, yes, yes.
Okay, thank you.
It's perfect. Yeah, go ahead.
First of all, good morning to all of you. First of all, let me introduce my paper over here. Basically, twice within the last 20 years, United States public health authorities have called for the elimination of the measles, and twice our collective efforts have fallen flat, right? So in that, basically my introduction of this paper here is that recently, as in view of the coronavirus disease, nowadays in the current scenario, right? So coronavirus disease COVID-19 has raised urgent questions about to mitigate and to develop the suitable analytical strategies to analyze the data and which were collected from the standardized protocol. And it becomes important to immediately assess the available data to learn what standard of care approaches are the most effective and evaluate it as fast as possible, right? So merging and cleaning of the data from the large multi-center hospitals is nowadays it becomes crucial, right? And that's why it requires the sophisticated data management. So, case reports form for the patient with suspected or confirmed COVID-19 patients are needed to collect and store their data in a standardized way. So, the objective of this study or this paper are to find out if it is possible to prevent or to delay the local outbreaks, just like the COVID-19, through restriction on travel from the abroad. The problem statement of this paper is that we are unable to collect the specific suspected information from the big data of the COVID-19 patients, and it becomes difficult to identify the symptomatic and asymptomatic patients during the this corona epidemic, and therefore it is difficult to predict the number of beds required or ventilators necessary for COVID-19 cases at this stage. So mathematical modeling is one of the important mathematical modeling plays and one of the vital role in this my paper. And so to develop a model, one must start with a set of data from a natural epidemic, and to test the model, one must apply it to at least one other epidemic, and most preferably, one should also suggest an intervention, and on the basis of the model, predict and verify its outcome. We must verify its outcome first of all. After that, right? And unfortunately, the available data on the incidence of the most of the diseases in most of the countries are below the accuracy needed, and we want to improve that accuracy by using the techniques of data science and machine learning. And so basically in this paper I'm using methodology from the linear algebra, and in the event that COVID-19 began to spread in India, I'm trying to develop a mathematical model that could mitigate the transmission of the disease. So one of the important thing is I'm using here that is called as the dimensionality reduction. So dimensionality reduction is a solution to the curse of the dimensionality. Dimension reduction models means the models which are based on the dimension reduction that reduces the size of the data by extracting the relevant information and disposing the rest of the data as a noise data. The most convenient mathematical language to express the data model is linear algebra only. So the main concept I'm using here is a singular value decomposition. It's one of the famous topic in the linear algebra, singular value decomposition. The singular value decomposition, let me explain first of all what the singular value decomposition is. And in my presentation, I will explain in the detail what that singular value decomposition is. So I'm first of all, I will explain you why there is a need to reduce dimensionality of the big data. So we are very much bored with the large volume of the data. So that's why it reduces the computational complexity with the less number of parameters, because we know that the parameters are increasing in each disease. It is totally dependent on the particular disease, particular epidemic. So it becomes important to reduce the computational complexity. Also, the cost-effective features are there. Azure interpretation is there, and it becomes simple to visualize the high-dimensional data having the salient features. So basically, I'm using the method here that is called the singular value decomposition from the linear algebra, which is a foundation for principal component analysis. In short, it is a PCA. So basically, this singular value decomposition is the factorization, or it is a decomposition of the matrix A. So A matrix having the size as a m cross n, having the rank as R, and there exists a factorization. This is the factorization U, sigma, and V transpose. This is the factorization of the matrix A, that is the given matrix, and where this U matrix is a m cross m matrix. U is a m cross m matrix where the columns of U are orthogonal eigenvectors of A transpose, right? Because as we are having the matrix A, we can easily find out the transpose of this matrix A transpose. We can easily find out, and the dimension of that matrix U, that is the size of that matrix, is a m cross m. Then sigma is a diagonal matrix where the columns of V are the orthogonal eigenvectors of the A transpose. Please note the difference between these two, that the columns of U are the orthogonal eigenvectors of the A transpose, and A transpose A, the columns of V are the orthogonal eigenvectors of A transpose A. And what is the sigma? That eigenvalues lambda 1 lambda up to the lambda r of A transpose are the eigenvalues of the matrix A transpose A. So that are the eigenvalues. And then this singular values sigma I, this matrix sigma, this middle, this sigma matrix is consisting of these square root of singular values, that is the sigma I, So that will be all in the diagonal entries, sigma 1 up to the sigma r. So these singular vectors and singular values having some properties. These A transpose and A transpose A having some properties. The first one, it is a symmetrical. Second one, it is a square matrix, and the third one, it has a least positive semi-definite. At least positive semi-definite. It means the eigenvalues are 0 or positive, and we are basically taking the advantage of that eigenvalues which are positive or 0. And both matrices A transpose and A transpose A are same positive eigenvalues, and both have the same rank R as A. And here I'm using the fundamental property of the symmetric matrices, which says that which are symmetric, we can choose its eigenvectors to be orthonormal. Because in the machine learning techniques, in the data science techniques, we have to orthogonalize, we have to standardize the data. So that's why I'm using the fundamental property of the symmetric matrices. After that, the singular value matrix is a unique. It is one of the important property of the singular value matrix. It is unique. It is unique, right? Then after that, it has a same size as the matrix A. Means whatever the given matrix A is there, where the data entries are substituted there in that matrix A, that matrix size and the singular value matrix A, it has the same size. Then it has a diagonal submatrix that contains the similar values, and it needs to be additional zero padding. Try to understand now what is the meaning of needs additional zero padding by here. Here, if it is totally depend on the m and n values, that is the size of the matrix, m number of rows and number of columns as a n. So if m is greater than n, if that is number of rows is greater than the number of columns, then such a type of situation will be there. You can see that here the additional zero padding you can see there, right? Here is additional zero padding from below this row, right? Additional zero padding is looking there, but it is only when the number of rows is greater than the number of columns, and when number of rows is less than the number of columns, then we have such additional zero padding. You can see that to this column, to see this side, to this column, there is additional zero padding is there, right? So it is totally depending on the number of rows and number of columns. It is totally depend on the number of rows and number of columns. And one of the important remark here is that SVD exists for any matrix A, because we know that in linear algebra or in abstract course, we are mostly many times we stuck when the determinant is 0, right? Many times we are stuck when the determinant is 0, but this exists, this SVD exists anytime, whether the determinant is 0 or non-zero, it doesn't matter. So this SVD exists for any matrix, so that's why it has a more importance. This method has a more importance. Now see how this SVD dimension and sparseness work. Now you can see that diagrammatically here, this is a given matrix. This is a given matrix whose entries are consisting of the number of patients or the depend. I will explain that model later on, but just try to understand this is the systematic theory for that singular value decomposition, how the dimension is going to be reduced. This is a matrix U. This is a sigma matrix. This is a V transpose, and this is the additional zero padding. You can see that this is this matrix. It is a additional zero padding. Now, in a moment, I will explain you that how that low rank, low rank approximation. We have to approximate the low rank because it is totally depending on that machine. How we are going to approximating that rank as a low here, because we have to basically what we are doing that we are adjusting or we are setting the smallest singular value to be 0. We are adjusting the smallest singular values to be 0. This is just the theory. I will explain you in a detail in the model. Whatever I have created that model in a moment, I will explain you. But this is just what the theory, right? And let us visualize this matrix A m cross n, U m cross m, sigma m cross n, and V transpose n cross n. That is the size of the matrices. And you can see that we can arrange the eigenvectors in different orders to produce U and V matrix. And to standardize, the standardization of the data is more important here in this my model. To standardize the solution, we order the eigenvectors such that vectors with the higher eigenvalues comes before those with the smaller values. You can see that here is a sigma 1 is greater or equal to sigma 2, and sigma 2 is greater or equal, and so on. So you can see that this is in the descending order. Highest priority will be sigma 1 here, and the lowest priority it will be automatically goes under decreasing on the diagonal, right? Okay, now let us take a simple example to understand or to elaborate more properly. So here is this example, counter example. So here is the matrix A, that is input matrix, and no matter it is a square matrix, it doesn't depend on the, it has a determinant 0 or may not be 0, no matter of that. But now see how that method is working over here. That matrix A is here. Now we can easily calculate A transpose and A transpose. That is not difficult part to calculate. Now, we can easily find out the eigenvalues of the matrix associated with A transpose, and also we can find out the eigenvalues associated with the matrix A transpose. Also, we can find out the eigenvectors associated with the matrix A transpose and associated with the eigenvalues lambda 1, 25, and 9. Right here, this is just simple calculations. Now we can find out the eigenvectors v1, v2, and v3, which are associated with these eigenvalues 25, 9, and 0. Right? Okay, so this is just the example. Now the singular values, right? We have seen before that singular values are nothing but the square root of the positive eigenvalues. So that is a, you can see that here is a 25 and 9, right? Lambda 1 and lambda 2, 25 and 9. So here I am taking the singular values, that is the square root of lambda I, that is square root of 25 and square root of 9, that is a 5 and 3. And therefore you can see that your decomposed matrix, is like this: U, sigma, and V transpose. Now the question will naturally arise is that where we are using this, is it right? Where we are using this singular value decomposition. So here are the some important applications. The applications are as following. The first one, that is my model I'm preparing for the same, and that is timely identification of the COVID-19 infected and healthy patient. Means we can classify whether it is infected and or it is a healthy patient. I will explain in a moment that how this model is working, but just here are the some important applications. Prediction of the situations through call recording, also we can do it. Also some image compression techniques in the, we can use that SVD. Also Google also use the page ranking algorithm by using this SVD. It heavily use the SVD decomposition over there, and it can, we can find out the structure in the movie rating and consumer. This is not the important application, but as in the current scenario, this is the important application, that we can timely identify the COVID-19 infected and healthy patient by taking the advantage of this singular value decomposition, because we can decompose the given matrix. Right now, let us see this first application, timely, how we can identify the timely the COVID-19 infected and healthy patient. So here is my basic model, that is from which we can predict the situations to be taken through the big data of the person having using this singular value decomposition. So first of all, I have, just for the understanding purpose, I have just taken a small data set. 1, 2, 3, 4, 5, 6, 7. Only 7 observations I have taken here with the some symptoms of the patient, that is taken from the World Health Organization website. That is a headache. That is the standard. What I say, standard symptoms of the COVID-19 infected patient. So that is headache, then runny nose, extreme sneezing, dry cough and sore throat, and fatigue and exhaustion and shortness of the breath. So these are just latent variable. I'm not taking the much variable over there. A lot of variable I'm not taking, but these are the some latent variable I can say. These are the latent variable. Now these are the number of observation. No matter, these observation may be large number, 1,000, 10,000. So at that instant only, also my model should be work, right? So, but just for the understanding purpose, I have taken here only the 7 observation. This is the column for the observation or the name of the person from the particular village or particular city, and the symptoms taken from the standardized protocol or the World Health Organization. My problem statement is that I cannot able to identify the classify the COVID-19 infected versus the healthy patient, right? So this is the data set I have taken from the World Health Organization data set. So this, what this entry exactly indicates, this entry 1, this entry indicates that this is the expert opinion. This is the expert opinion taken from the expert doctor of that COVID-19 hospitals, right? So this one entry, these ratings basically are from 1 to 5. These ratings are basically from 1 to 5. So 1 means it has a less headache, right? Means a mild headache, right? So this, what this 5 entry indicates, this Anil has headache as a severe headache, 5, right? So this is the expert opinion taken from the doctors, right? So this 5, second 5 is also the it is a runny nose, right? Also dry cough, it is a dry cough, it is a severe dry cough, right? Also it has 0 means what, it is a fatigue and exhaustion. The shortness of the breath, again, it is the no shortness of the breath, right? So this is the my data set. I hope you have understood this data matrix here. So now I'm taking this matrix, I'm shifting this matrix into the A matrix. That is what I have to now. So now see this A matrix. This A matrix, just the entries are taken from this. See, 11100. You can see that here. 11100, right? This column row. So I have shifted that entries over here in the matrix A. Now I have decomposed that matrix A into the U sigma and V transpose. And now this diagonal entries I have explained you before that. Here this is the square root of the lambda I, right? Square root of the eigenvalue, that is the singular values, and that is the square root of singular values, square root of eigenvalues 9.64 and 5.29. It is in the decreasing order, is it right? This is in the decreasing order, 9.64, then it is a 5.29. As this data set is a small only, just for the understanding purpose, but whenever there is a large data set, then this matrix will be more larger, is it right? So this is 9.64, 5.29, and this 9.64, it represents the strength of the specific symptom. Means runny nose, what is the strength of that? Headache, what is the strength of that specific symptom? Right? Now, here, how exactly dimension reduction is going to be done? So the answer is, for that, I have already explained you, we have to set the smallest singular values to be 0. Means whatever the smallest singular values are there, out of that, you have to set it to be the smallest singular values to be 0. Now see, this is the matrix, this is the reduced matrix, or this is the factorized matrix, right? Now see how I can reduce the dimension by setting the smallest singular values to be 0. Now you can see that this is exactly the dimension reduction is going on, because as this 5.29 it becomes 0, because this is a less value than the 9.64. As this becoming to be 0, so as this is the 0, so automatically while multiplication, this entries will becomes automatically become 0 while multiplying, right? So in this way the dimension reduction has been done. So this column, this column, this row, this column, and this row, right? So these three becomes 0 only, and then we have this matrix only, right? We have this matrix only. Now you can see that this is just noisy data we have taken, and unnecessarily we are increasing the size of the particular data sets in our machine, right? So in this way, by using, also we can timely identify the COVID-19 infected patient by looking, by applying the COVID-19 infect, by applying the techniques from the machine learning or the data science or the linear algebra, that is by singular value decomposition. So that's all about my model, and the conclusion is just we can extract, or we can extract the relevant summaries from quickly and most efficiently, and it becomes more and more easier to visualize the high dimensional data when reduced to very low dimension such as 2D or 3D. We can easily extract the relevant summaries and most efficiently by reducing the space complexity, and the new direction revealed what I say so that will be more affordable way to reduce the future pandemic. And then it becomes, or then it will look at how countries can reduce or mitigate and adapt to the future pandemic and the climate risk also. And it will also update the reporting guidelines for the observational studies. And so this requires this is totally based on the COVID-19 scenario. This model will is basically working on the COVID-19 patients only. So the data set whatever we are collecting from the standardized protocol, we are working on that. I'm working on that, and it is possible to take the right actions quickly, and then we can save our life and also save people's lives in our community by preventing the community spread of the virus, any spread of the virus, right? We can deduce that around few percent of the infected patients will require intensive care unit, that is ICU, right? And half of those admitted in the intensive care unit until we require the mechanical ventilation. So over time, once the model is validated, appropriate numbers can be generated for the healthcare planning. So basically, this visualization of the data. So in short, my summary is that so visualization of high dimensional data is possible. Also, appropriate numbers can be generated for the healthcare planning, and it becomes possible to identify the infected and healthy patient during the corona epidemic. And that's all about my presentation on my paper here. So most of the information I have taken from the book, The Mathematical Problems in the Data Science, from the ISHM. I have took the inspiration, or I have taken the most of the information or most of the knowledge I have taken from this book only. Also, I have forget to write down the name of the famous author, that is the Gilbert Stein, Professor Honorable Gilbert Stein, where he have explained the concept of singular value decomposition in his book very well. So I forget, sorry for that. I have forget to mention in the bibliography name of that professor, Gilbert Stein. And also mathematics for machine learning, I have taken the help of that book also. And thank you. So that's all about. So if you are having any questions, please ask, sir.
Yeah, thank you, Dr. Hatare. If there are any questions from the audience, I'll be happy. And he would be very happy to address as well.
Yes, sir. Yes, sir.
So you were mentioning towards the end of the conclusion that if the model is validated, so does it mean that you have constructed some model and that needs some validation, or?
Yes, sir. Because I'm coding for the same, sir. In the Python language, I'm coding, but I'm stuck somewhere. But I will do in a few days. I will do that. I'm not having sufficient time to give over that, but I'm trying to do that, sir.
No. Modeling is different from coding.
Yeah.
Have you constructed some new model? Is my question.
Yes, sir. This is the model, but this is just for the small data set. But how I can prepare the data model for the big data set? So that is the problem here, and that's why we have to create one such a model, or I'm creating such a model which will be work on the large data set.
Okay.
Okay, sir.
Okay, thank you. If there are no further questions, we invite the next speaker, Professor M.D. Srinivas. Professor M.D. Srinivas got trained as a theoretical physicist, and then over a period of time, he developed a serious interest in studying Indian civilization, and for the past more or less 3 decades, he has been studying very seriously about the Indian tradition of sciences and technologies. In particular, he has worked on various aspects of Indian tradition of mathematics and astronomy. In fact, I am one of the beneficiaries of having associated with him. And Professor Srinivas has also been keen in Indian scientific tradition and technological tradition, that they should be actually integrated with the school curriculum. So we had myself, Professor Sriram, and Professor Srinivas, all the three of us had an occasion to present a series of lectures on the development of mathematics in India. And besides that, he has been studying several other aspects of Indian civilization studies. So without spending much time, it will be a pleasure to listen to Professor Srinivas. So he will be speaking on one of the interesting constructional methods of pan-diagonal magic square, which Narayan Pandita has given in his Ganita Kaumudi. Professor Srinivas, please.
Namaste. Thank you very much, Professor Ram Subramanian, for the very kind introduction. So I will be speaking on the Samputa Vidhi, or the folding method of Narayana Pandita for the construction of magic squares. So Bhadra Ganita is the name for magic squares in India, study of mathematics of magic squares in India. And this was fairly popular in the general populace, with the general educated or school educated people, and even uneducated perhaps till a century ago. The first chapter of Srinivasa Ramanujan's notebooks, maybe I will display it towards the end of the talk, is on magic squares. Professor T. Vijayaraghavan, a very eminent mathematician in the first half of the last century, who was the first director of the Ramanujan Institute in Chennai, he wrote an article on the Jaina magic squares in 1941. There he displays this 4x4 magic square. And he says when he was 9 years old, he learned this magic square from an elderly person who had not been to school at all. So this should convey to you how Ramanujan ended up with magic squares, how Vijayaraghavan ended up with magic squares. That the magic squares were very popular in Indian culture till the early decades of 20th century. And Indian mathematicians specialized in a particular kind of magic squares called Sarvato Bhadra, or what are called pan-diagonal magic squares today. So what is a pan-diagonal magic square? A magic square is one where the sums of every row and sums of every column are constant. That is called a semi-magic square. If in addition, the two what are called the principal diagonals, if they also add up to the same sum, then that's called a magic square. But a pan-diagonal or a Sarvatobhadra square is one where what are called the broken diagonals. So you start from 10 here, 10, 16, then you cannot go beyond. So you have to come back here to 40, 34. So 10, 16 plus 40, 34 also adds up to 100. This is a very famous, very ancient magic square in India known as Nagarjuniya. It adds up to 4 cross 1 magic square adding up to 100. So there are all these are the two principal diagonals. All these are what are called Alpashruti, or the broken diagonals or the little diagonals. So if you mathematicians tend to think of these as being embedded on a torus. That is, you identify the top edge with the bottom edge. You identify the left edge of the square with the right edge. So then when you go from 32, 44, 18, then you go up, you come up with this 6. So this is a pan-diagonal square. Now, a brief overview of the development of magic squares in India. The name Bhadra Ganita, actually it's an auspicious combination of numbers. That is what it means. Even in the Islamic tradition of mathematics, which did an extensive study of magic squares, they were called harmonious combination of numbers. But it's only in the West, medieval and early modern West, the world, these squares acquired somewhat of a negative connotation. They started being called magic squares, which is for some evil purposes and kinds of things. Anyway, from very ancient times, magic squares have been talked about in India. The 3 cross 3 squares have been discussed and attributed to the ancient astronomer Garga. We all know of the Loshu magic square in China, which goes back, according to Chinese tradition, to a couple of centuries, millennia BCE. They were spoken of in the Chinese texts around 3rd, 4th century mathematics texts even. The work called Kakshaputa Nagarjuna, only citations from this are available. That gives a method of construction of 4 cross 4 magic squares. And in the case of an even sum, the method of construction given by Nagarjuna actually leads to a pan-diagonal square. A very famous text called Brihat Samhita of Varahamihira, written around 550 of the Common Era, has an interesting chapter called Gandha Yukti on perfumes. In this chapter, it deals with the calculation of binomial coefficients by what we today call the Pascal triangle. And it also deals with 4 cross 4 pan-diagonal magic square for constructing harmonious combination of perfumes to get what are called Sarvatobhadra perfumes. So by about 550 of the Common Era, Indians knew a large number of 4 cross 4 pan-diagonal magic squares. There's a commentary of Bhattotpala, who hailed from Kashmir in 950 on Brihat Samhita, where he actually describes some of the very interesting properties of these 4 cross 4 pan-diagonal squares, which were rediscovered in the 20th century by Rosser and Walker. Pan-diagonal squares were also very common in public places in India. The 10th, 11th century Jaina temples in Dudhai, if you go to YouTube, you will find a very broken version of the temple currently. It's near Lalitpur in Uttar Pradesh. And in Khajuraho, the Parshvanatha temple there has a 4 cross 4 pan-diagonal magic square. Magic squares were seen on Gwalior Fort, etc. Coming to mathematical works, the first mathematical work which we have so far seen, which talks about magic squares, is a Prakrita work. It's actually in the Apabhramsha language. Ganita Sara Kaumudi by Thakura Peru, who lived around Delhi. His book has only about 9 verses on magic squares, which he calls Jantra. This has been edited and translated by Sakya, meaning S.R. Sharma, Kusuba, Hayashi, and Yano. And he classifies magic squares into doubly even, that is numbers which are multiples of 4. Singly even, that is numbers which are of the odd type, 4n plus 2, that is 6, 10, 14, etc. And odd ordered squares, that is 3, 5, 7. And he indicates a few methods of construction. But the most important work, Indian work on magic squares is the celebrated work called Ganita Kaumudi of Narayana Pandita. Yesterday, Professor Ram Subramanian, day before yesterday, explained to you how it's about 3 times the size of Lilavati and what kind of contents it had. And this discussed many of the beautiful verses and the mathematics contained in there. We will speak about it quite a bit today also. Chatura Chintamani of Giridhara Bhatta is another mathematical work which has been edited and translated by Hayashi of 16th century. It has a very brief section of 6 verses on magic squares. Apart from mathematics texts, various Jaina stotras have very interesting description of the yantras, and they have several kinds of magic squares, 4th order, 8th order, 12th order, and things like that. Tijabahutta stotra of Manadeva Suri, stotras of Sundara Suri, Chatushashti Yogini Mandala Stuti of Dharmanand, all these, some of these magic squares are displayed in a very famous article of Datta and Singh on magic squares, which was revised by Professor K. Shukla and published in 1992. The Compendium on Indian Law, written by Raghunandana in Navadvipa, one of that is called Smriti Tattva, that also describes a method of constructing 4x4 magic squares. Now coming to a brief summary of Narayana Pandita's Ganita Kaumudi. It has about 50, it's the 14th chapter of Ganita Kaumudi is devoted to Bhaddha Ganita, 57 verses and 17 verses of examples, 57 verses giving rules. So first he gives this classification Samabharga, Samagarbha magic squares, that is magic squares of the order 4n, Vishamagarbha of the order 4n plus 2, Vishama odd order. Then he discusses how magic square mathematics is closely intertwined with the Kuttaka, because the magic squares are to be basically constructed on the basis of arithmetic sequences or Shredi, as Professor Ram Subramanian explained. And so he solves this linear indeterminate equation to tell you the relation between the order of the magic square and the total sum that is required and the kind of arithmetic sequences that can come into play. Then he discusses the method which was discussed by Professor Ram Subramanian of how to fill in a 4x4 pandiagonal square by means of Turaga Gati or horse moves. He displays 24 such squares and then concludes by argument that there are 384 such pandiagonal squares, a conclusion that was again arrived at in 20th century mathematics. In 1693, Frenikel listed all the 7040 magic squares of order 4, filled by 1, 2, 3, 4, etc., 16. And Rosser and Walker showed that there were only 384 pandiagonal magic squares of these 7040. Some of the interesting properties that were discussed by Bhattotpala were rediscovered by Rosser and Walker. Professor Vijayaraghavan, whose paper of 1941 I alluded to earlier, he discovered a very interesting property connecting the neighbors of an element with in a 4x4 pandiagonal square. And I will perhaps be able to tell you how this result of Vijayaraghavan leads to a very simple method of constructing 4x4 pandiagonal magic square. Then Narayana goes on to give 2 methods for constructing each of the 3 classes of squares, that is doubly even, singly even, and odd. One of the methods for odd squares, which is a movement along the small diagonals or Alpashruti. This is an ancient Indian way of constructing odd order magic squares. It was popularized in Europe by Simon de la Loubre in 1691. But Narayana's revolutionary discovery was the Samputa Vidhi, or the method of folding, where he generates a large class of doubly even and also odd magic squares by composing 2 simple magic squares. So it's an extremely beautiful mathematical construction. Incidentally, de la Loubre also talks about composition of 2 squares in his report, but he does not attribute it to Indian sources. Such methods were soon to be considered in Europe, especially in France, by Pinard, de la Hare, Sauvier, etc., and later by Euler in 18th century. And this approach of constructing magic squares by composing 2 simple magic squares is indeed the preferred and standard way of constructing magic squares in contemporary also. Now it's very interesting to note, I think I will have time to show you, that the templates used by Narayana for the construction of doubly even squares by folding method actually lead to what have been very popularly studied recently in the last 2-3 decades as the most perfect magic squares. Similarly, for the case of odd squares, A simple alteration of the templates used by Narayana leads to beautiful magic squares which are pan-diagonal and associative. They have been studied under the nomenclature ultra magic squares. So first we straight away go to the Turagagati method, which Professor Ram Subramanian explained in detail. So in this verse, where he's talking that we use the horse movement, take the arithmetic sequence, divide it into pairs of pairs, dvau dvau. And then from the arithmetic sequence, so it is broken into first 4 sequences of length 4 each, and each such sequence of length 4 is broken into 2 pairs. And then they have to be placed. And then he mentions krama, utkrama, koshthaikya, ekantara. And sabya, asabya, turangamaritya, kosthana, prapurayet, ankai. So by this method, you fill in the cells. And then he of course says that in a 16 in a 4x4 magic square, this is the method. Then he says the horizontal, the vertical, and all diagonals. He is using not just the dvivachana or the karnas. So all diagonals, including the smaller or the broken diagonals, their sums add up to the sum of the magic square. So he really does not describe the method, and one has to look up his examples and his very brief Vasana Bhashya to understand what his method is. And actually, to illustrate his method, Narayana goes ahead and displays, as was discussed by Professor Ram Subramanian and Surya Narayanan, he displays 24 half-filled squares like this. And it is by studying them and by understanding what he means by Turangama Ritya, what is meant by the horse move, by understanding what is meant by Krama and Utkrama, and what is meant by the Koshthaikya and Kosthantara, one should reconstruct them. Earlier attempts to reconstruct that was by Professor Shukla and in his revision of Datta and Singh, maybe it goes back to Datta and Singh, that they discuss Utkrama as saying that the second half of the 4, 5, 6, 7, 8 should be thought of as 5, 6, 8, 7. And 1, 2, 3, 4 should be thought of as 1, 2, 4, 3. That's the order in which they should be filled. That's one interpretation. But it's a complex algorithm which is not fully discussed in Professor Shukla's or Professor Parmanand Singh's works on this subject. Later on, there has been an attempt by Dr. Bhaumik, and she had tried to use this kind of thing. 4 to 5 is an adjacent movement. And then 3, 2 to 3 is a diagonal movement. And so using that kind of movement for Koshthaikya, she has tried to give an algorithm. Again, that's not complete and it's fairly complicated. What Professor Ram Subramanian Surya Narayana discussed yesterday is an algorithm which is based upon only horse movements. So for these 6 magic squares, we can see that these sequences of horse movements completely generate the first 8 places and then they can be completed. For instance, take this last one here and take the last row here. 1 to 2 is a downward horse movement. Then 1 to 3, not 2 to 3. 1 to 3 is a leftward horse movement. Then 3 to 4 is an upward horse movement. So DUU. And then 1 to 5 is a rightward horse movement, R. And the second half is again DUU. And in fact, this is one of the very simplest magic squares. This was first displayed by Narayan Pandita. And later on, he gave these 24 templates. Now I come to the 20th century studies of 4x4 squares. So Rosser and Walker, Narayana using this concluded that we have he showed 24 magic squares with one at the top left corner. If the magic square is pan-diagonal, it can be cyclically permuted either through rows or through columns. And so what Narayana could show was this number 1 can be placed anywhere by a cyclical movement of the rows or columns. And you will get again 24 squares by the same construction. So 24 into 16 was 384. That's how Narayana concluded that there are 384 pan-diagonal magic squares of order 4. So what Rosser and Walker, they first showed this property that in a 4x4 pan-diagonal square, every subsquare adds up to the magic sum. So it is 1 to 16 you fill, you get 34 as the magic sum. 1 plus 12 plus 5 plus 15 plus 6. This adds up to 34. 1 plus 12 plus 14 plus 7. That is also a subsquare because this edge is identified with this edge. And 12, 13, 6, 3 is also adding to 34. So every 2 cross 2 subsquare, I mean the magic square is put on the torus, adds up to 34. This was the Sarvatobhadra property that was enunciated by Bhattotpala in the 10th century. The second very interesting property, this also I am sure was known to the ancient Indians, because the Nagarjuna method of construction is essentially based upon this principle. In a pentagonal 4 cross 4 magic square, the sum of any entry with another which is 2 squares away from it along a diagonal is always half the magic sum. So 1 plus 16 is 17, 15 plus 2 is 17, 4 plus 13 is 17, 10 plus 7 is 17. So you move along any major principal diagonal or small diagonal, you take 2 steps. The sum of those 2 terms is 17. So this is a very beautiful property. It immediately tells you that if you had a magic square with an odd sum, then half of the magic sum will not be an integer. So sum of these two, one and the element 2 places away from it, will be half of the magic sum. So if the magic sum is 35, this will have to be 17 and a half. So integral magic squares of 4 cross 4 order with a magic sum of an odd number are not possible. Then Rosser and Walker, again, as I told you, discussed this 384 total. Now, what is the beautiful work of Professor Veer Raghavan? So it was shown that if you have a 4 cross 4 magic square, there is a relation between any element and what are called its 4 neighbors. So these two, EG and BJ, are the 2 neighbors of the element F, one along the row, another along the column. So if 2S is the magic sum, they should always obey. From the conditions of pan-diagonality, you can show they should always obey this relation. So Vijayaraghavan also proved, in particular, for a magic square which is filled in with 1 to 16, all the 384 versions, 16 has as its neighbors 2, 3, 5, and 9. Or this is true for every element. It has a fixed set of 4 neighbors. So using this Vijayaraghavan property, it becomes very easy to construct a magic square. So let me just very briefly show you. So I can place my 1 anywhere, but let me choose to place it at the top left corner. Then from the property 2, the 2 steps away diagonally, that element should add up with 1. The total should be 17. So this becomes 16. And from Vijayaraghavan's property, 2, 3, 5, 9 should always surround 16. So in first step, I will arrive at this. The moment I put 1 here, this 16, I can choose this 2, 3, 5, 9 in a different order. So we will get 16 different 4 factorial, 24 different magic squares with 1 at the top left corner. That's what Narayana showed. Now I use the property 2. 5 is here, so 2 steps across, I have to put 12 here. 9 is here, so I have to put 8 here. 3 is here, I have to put 14 here. 2 is here, I have to put 15 here. So this much of the magic square is filled. The rest can easily be checked. You have to have a total of 34. 13 will come here. Any subsquare will have to add up to 34. So 11 will have to come here. So like that, you can fill in the magic square. It's the simplest way that any school student can show in the construction of magic square. Another very nice thing Professor Vijayaraghavan did was the following. That the pan-diagonality actually is 16 conditions. 8 rows, 4 rows, 4 columns, 2 principal diagonals, and 6 broken diagonals. So the pan-diagonality condition is a 16 condition adding to the same magic sum. But of these 16 conditions, only 12 are independent. So a 4 cross 4 pan-diagonal magic square can be parameterized by 4 independent parameters and the magic sum yes. So Vijayaraghavan gave this construction where he chose A, B, P, and R as the parameters. This is looking somewhat complex, so I just wrote a simpler version of this. Choose A, B, C, D as your 4 parameters and X as another parameters. These 5 parameters fix the magic square. The magic sum will then be given by QS is equal to A plus B plus C plus D. And for D, S minus D should come here. For B, S minus B should come there. Half the magic sum. 2 diagonally distant elements 2 places away should add up to half the magic sum. Now I just constructed one interesting magic square. We can call it the Mach theta magic square because we are celebrating Ramanujan's birthday today. Ramanujan in his letter of 12 January 1920 announced this discovery of Mach theta functions. So you put 12, 1, 19 and 20. So A is chosen as 12, B is chosen as 1, C is chosen as 19. If this does not add up to an even number, no pentagonal square would be possible with this. They adds up to an even number, fortunately. And by a suitable choice of X, we are able to construct this. And it's also a very interesting square because it is not filled by 4 normal arithmetic sequences. It is filled by what are called generalized, 4 generalized arithmetic sequences. Maybe we will discuss this in some other occasion. Now, straight away come to other constructions of Narayana Pandita, higher order magic squares. The standard method for approaching them was earlier to construct any 4n cross 4n magic square, use a template of 4 cross 4 magic square, divide the larger magic squares into blocks of 4 by 4 and fill them in a similar way. So this is, for instance, discussed in the book of Takuraperu, the Ganita Sara Kaumudi. I am just discussing that method. This is also discussed in Narayana's Ganita Kaumudi, a slightly different method he discussed. So you use this 4 cross 4, which is one of the 24 or 384 magic squares discussed by Narayana. Put 1 here, 2 at the same place, 3 at the same place, 4 at the same place. Now the next 4 set of numbers you put at corresponding places in these 4 other 4 blocks. Then you go back like this. You have come like this, then you go back like this. So you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then from here, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. They should be filled at places where 5, 6, 7, 8 are here. So you have constructed half the magic square this way. This is the entire completed magic square. It's an 8 cross 8 pentagonal square with a sum of 260. And you can also see, apart from being pentagonal, it has this other property that every sub-diagonal adds to 130. Every sub 2 cross 2 square adds up to 130. But that does not make it a most perfect magic square, what is called. I'll come to it in a moment, where every element with an element 4 steps away along a diagonal should add up to 65. Here, only 2 steps away along the diagonal add up to 65. So this is not a most perfect square. Now we come to the topic of the day, Narayana's Samputa Vidhi. So in 4 verses, Narayana discusses this approach, first for doubly even magic squares. Now the method is, I will skip the translation in the verse. We will explain the method with an example. And we will straight away go to an example of an 8 cross 8 magic square, adding to 260. Narayana says, first you take a simple sequence of your choice. Then from that you make another sequence. All sequences are length 8. Instead of 1, 2, 3, 4, 5, 6, 7, 8, you can choose 2, 3, 4, 5, 6, 7, 8, 9 or any other arithmetic sequence of length 8. And from this you reduce by 1 or reduce by some standard amount. Construct this second sequence. Mula Pankti, Para Pankti. Now the sequence should be so chosen. The problem is given is to construct an 8 cross square adding to 260. So these sequences should be so chosen that 260 minus the sum of the Mula Pankti divided by the Para Pankti should be an integer. If that's not possible, then such a construction is not possible. Guna Pankti is one where this integer multiplies the Para Pankti. So this is the preparation. So at the end of the preparation, you have 2 sequences, Mula Pankti 1 to 8, Guna Pankti 0, 8, 16, 24, etc. Then Narayana says these 2 Panktis should fill 2 squares. One is called Chadya, the covered. Another one is called Chadaka, the coverer. So you have to imagine them as if you are folding your hands. So one sits above the other, or a door is being closed. So the 1 to 8 are first filled in the top half of the square and in the bottom half of the square. In the top half of the square, you fill them clockwise. In the bottom half of the square, you fill them anti-clockwise. Narayana says one is going up, one is coming down in its verse. Mula guna ke pankti yete badhrardatastu parivrite. Tiryak koshtagatani, no, here. Urdhvasthitaihi tadankaihi chadaka sankyo. So in the one half, you put them in ascending, descending order. In the second half, you put in descending, ascending order. The other pankti, that is the Guna pankti, that is to be put now. You divide the magic square into left half and right half, and you put them in an anti-clockwise here and in a clockwise way here. 0, 8, 16, 24, 32, 40, 48, 56. 0, 8, 16, 24, 32, 40, 48, 56. This way. So mathematically, if you see, you fill the same Shadya pankti or the covered with this sequence. In place of 1, you put 0. In place of 2, you put 8. And then take the transpose of it. Then you will get the Chadaka square. So these are the two squares. Then he said you fold. By folding, he means you add 4 with 56, 5 with 48, 4 with 40, 5 with 32, this 4 with 0, this 5 with this 8, this 4 with this 16, and finally 5 with 24. Similarly in the next rows, and then you will get this square. Instead of folding, you can add them as matrices. Because these are symmetric, you will also get another 8 cross 8 magic square, which is a different magic square. Narayana displays that also. So in this case, folding can be just adding also in this particular case. I mean, the composition can be just adding also. So this is a very beautiful square adding to 260. Here, every 2 cross 2 subsquare adds up to 130. That is half the magic sum. And any pair of elements which are 4 places away along the diagonal add up to 65, which is 1/4 the magic sum. So with 1, you come 4 steps, 52, 22, 34, 65. It adds up to 65. 24 to 4 steps, you come to 41. So these magic squares were, they were somewhat defined in the end of 20th century by an American mathematician, but they became very popular in the last decade of 20th century by Dame Oler and Shah, who wrote a book on this. She called them most perfect magic square. A most perfect magic square is of a doubly even order always, 4n cross 4n. Every 2 cross 2 subsquare adds up to 1n the magic sum. Every 2 elements which are n by 2 cells apart along any diagonal, including broken diagonal, add to 1 by 2n magic sum. So the second condition immediately implies that the magic square is also pan-diagonal. So that can be added to the condition. So clearly, every 4 cross 4 pan-diagonal square is most perfect. The question is about higher order magic squares. There are not too many of them, but of course there are indeed a whole lot of them. And these constructions have been discussed by Oler and Shah. Unfortunately, she doesn't know about Narayana and she doesn't talk about him. Though the Wikipedia page today talks about the fact that Narayana discovered a most perfect magic square like this. And every construction using Narayana's template like this always leads to the template. If it is like this, you use any arithmetic sequence and then make a parapankti and do all that, you will always get a most perfect magic square. And you will similarly for 12th order, 16th order, you can construct. So Narayana's method is indeed the most beautiful and simple way of constructing 4n cross 4n most perfect magic square. You can use folding method to construct other kinds of magic squares of higher Samagarbha. I will not discuss that here. You will immediately go to odd order. So here also Narayana discusses this. Narayana first discusses the old method of constructing magic square by moving along the small diagonals. Then he gives this folding method for magic squares of odd order. This again we will discuss with an example. This is much simpler. The templates are very simple. So 5 cross 5 square adding to 65. Choose your Moola Pankti as 1, 2, 3, 4, 5. Para Pankti as 0, 1, 2, 3, 4. If you have to get 65, 65 minus sum of the Moola Pankti divided by Para Pankti is chosen such that it's an integer. Multiply the Para Pankti by 5, get this Guna Pankti. So you are using this sequence and this sequence to fill in 2 templates of 5 cross 5. The central row column, you fill it with 1, 2, 3, 4, 5. You fill it here with 0, 5, 10, 15, 20. Then move along, fill the next cyclic permutation, fill the next cyclic permutation. Then you have to come here, next cyclic permutation, next cyclic permutation. Then same thing is done here. So here Chadaka and Chadya are the identical templates. Only One is filled with Mula Pankti, another is filled with Guna Pankti. And then you fold them. And you get this beautiful magic square. Now, unfortunately, though it's a very nice magic square, it is associative. That is, you along the central element, any two elements which are equally distant add up to twice the central element, and they add up to, if it's a 5 cross 5 magic element, they add up to n squared plus 1. So 23 plus 3 is 26, 20 plus 6 is 26, 5 plus 21 is 26, 13 is the central element, 26. Here, every row, every column, two diagonals add up to 65, but this is not pan-diagonal. 20 plus 10 plus 25 plus 15 plus 5. This leads to 35. This is all right. Let us take another sum. 24 plus 22, 46 plus 25. Already you have gone to 71, 94, and 150. So this is not pan-diagonal. But we can make a very simple modification of Narayana's method, basically of this template, to immediately lead to a pan-diagonal square. So what is to be done? 1, 2, 3, 4, 5 stands where it is. Instead of putting the second permutation here, you put the immediate first permutation of it here. You put the fourth permutation, that is the one here. So, or it can be called the third permutation, whatever you call. 4, 5, 1, 2, 3 here. Then again, 4, 5, 1, 2, the fourth one. 2, 3, 4, 5, 1. The fourth one, 5, 5, 1, 2, 3, 4. Then the fourth one, 3, 3, 4, 5, 1, 2. So you change the Chadya template, change the Chadaka template also in the same way, and then you do the folding. You will get a magic square, which is a very beautiful pan-diagonal and associative magic square of order 5. Pan-diagonal means rows and columns, and all the broken diagonals add up to 65. Associative means about the central element, elements which are symmetrically situated add up to n squared plus 1, that is 26. Such a pan-diagonal and associative magic square of odd order is what is called an ultra magic square. So, by a very simple modification, just for curiosity, 5 cross 5, there are 28,800 pan-diagonal squares out of a total of 22 crores, 220 crores, which are the number of magic squares of order 5 with entries 1 to 25. And this has some other beautiful property. Any element with 4 elements around it, you add it, you will again get magic sum. So 5 plus 7 plus 11 plus 23 plus 19 is magic sum. Another thing is, any element with the neighbors also adds up. 5, 24 plus 6 plus 17 plus 13 plus 5 is also magic sum. So now odd orders which are not divisible by 3, this method is applicable. But odd orders which are divisible by 3, I will only speak for 1.5 to 2 minutes, is a problem. There are really no pre-modern examples of pan-diagonal squares of 9th order or 15th order that I am aware of, or one you can easily find in the literature. In 1875, Reverend Andrew Frost, he was a missionary in Nasik from 1853 to 1869. Then he went back to England. Then he wrote a paper on general properties of Nasik squares. He used the term Nasik square for pan-diagonal squares. Earlier, De La Hire, etc. used the name perfect magic square. But the more common name in European magic tradition was, they were called diabolic magic squares. Rosser and Walker's paper calls them diabolic magic squares. Another name was Jaina magic square because these squares were found in the Parshvanatha Khajuraho temple. But today the common terminology is pan-diagonal. So Frost constructed a magic square of order 9 and 15. Now there are quite a few methods. Margosian's book of 1908 to a recent paper of Nordgren in 2012 discuss several methods which are akin to folding, but they are not directly folding. But we can generalize the folding method by changing this sequence 1 to 3 times 2k plus 1 by permuting it in a suitable manner, in a very simple way. The rule is simple. You divide it into succession of triplets which are alternatively direct and reverse in order. Flip the first 2 and last 2 elements. Then you have the Mula Pankti like this. Para Pankti is similar. and you use the fourth permutation to fill up the successive columns. Then you will get pan-diagonal square. So for instance, for 15 cross 15 square, the Mulakam key should be 2, 1, 3. You flip the first two elements, 1, 2, 3, 6, 5, 4, 7, 8, 9, 9, 10, 12, 13, 15, 14. You flip it here. 9, 7, 8, 9 in direct order, 12, 11, 10 in reverse order. Flip the last two, first two elements. And then you fill up the Chadyaka and Chadya Panki. But use the fourth permutation. And here is a construction of 9 cross 9 square. And similarly, you can construct. So this is perhaps the simplest way to construct 3 into 2k plus 1, that is odd multiples of 3 orders, also by a simple modification of the folding method. I will skip Ramanujan. I will say something about it in the talk on Ramanujan. So these are Ganita Kaumudi, Rasarvakar, Vijay Raghavan, Datta and Singh, thesis of Kusuba on Narayana Pandita, Olaran Shah's book, Chatura Chintamani, Ramanand Singh's translation of Ganita Kaumudi, Takura Peru, 2 papers on folding by Professor Raja Sridharan and myself, which discuss some of the proofs how Narayana's constructions lead to beautiful magic squares. Paper on Nodgren, recent review article of Hayashi. These are references. Thank you very
much. Thank you, Professor Srinivas, for this wonderful overview on magic squares. If there are questions, maybe 1 or 2 can be permitted, short questions. I have one query. This you were mentioning in the beginning about this Garga. So do we find verses describing, or is it some alluded somewhere?
I have requested the only authority on Garga currently in India, Professor R.N. Engar. He has not seen in, it does not exist in this Ruddha Gargiya Samhita that he is editing. This is perhaps there in an astrological work of Garga, which has to be seen. So we have not yet. Everybody, all review articles in India on magic squares do talk about it. Kaman talks about it, and Hayashi, but they don't mention where they first got this statement that Garga has the magic square. So we don't know. And the name Kachaputa is very interesting. The Loshu magic square also was revealed. Kachapa means a tortoise. It was revealed on the back of a tortoise coming from the sea to the Chinese emperor. So the Indian name Kachaputa and the Chinese Loshu magic square have a consonant. And Garga's magic squares are also 3 cross 3 magic squares.
Yeah, well, just a comment. So you are referring to as Kakshaputa rather than Kachaputa. Kachaha is obviously tortoise. This Kaksha is a very rare occurrence. So I was just wondering whether it could be Kacha. No,
people were referred to this Nagarjuna's work are using Kakshaputa. But Kachaputa occurs in Varahamihira's Brihat Samhita and our commentary of Bhattotpala. And perhaps Nagarjuna's work might have been in Padiyar. The work has not been seen. It has been quoted by one Gunatilake in the middle of 19th century. The verse Arka Indu Nidhanari Tena Lagna Vinasanam, on which that thing is done, was quoted by Gunatilake. And in Nagarjunia is also there is a verse, but they are in Sanskrit. So perhaps they have converted that into some Sanskrit word, Kakshaputa. We don't know.
So I think if there are no further questions or comments, so I would like to hand over the floor to Professor Sriram to conduct further proceedings of this conference. So we thank all the speakers of the forenoon session. So we had a very interesting session starting with Jonathan Crabtree and ending with Professor Srinivas.
Okay. Good. Yeah. It's very good. Thank you. Unfortunately, I could not be present for a major part of the previous session because I was giving a talk elsewhere. But whatever I have heard, some part of it, maybe 25%, they are all very good. So I thank all the speakers and the chair of the session, Professor Ram Subramaniam. So that's good. So now we'll move on to the valedictory session. Okay. So, okay, everybody is ready for valediction. Okay. So first, I think there'll be a presentation again by today is, as everybody knows, it is Professor Srinivas Ramanujan's birthday. So a lot of celebrations are going on. Many societies and departments and universities, etc., have organizing functions. So we couldn't do anything special, but we thought we'll have at least a short this thing, talk on Srinivas Ramanujan. So I request Professor M.D. Srinivas to give this talk. I am very thankful to him for agreeing to give this talk at a very short notice. Yeah, please. Yeah, Professor M.D. Srinivas.
Thank you very much, Professor Sriram. Really claim to talk on Srinivas Ramanujan, as I have not studied his mathematics at all. So I will try to do some justice to some historical questions in relation to Ramanujan. How is it that our assessment of him has changed through the last century? And one or two interesting questions as to how do we understand his mathematics? How has the world viewed the method of Ramanujan for obtaining his result? You can just stop me at any point, because there is no, you just give me a 2 minutes notice to conclude. Very well. So this is all well known that Ramanujan became acquainted with the plane trigonometry of Loni and cos synopsis. But what is most interesting is by the time he was in school, towards the time he left school, around 1903, 1904, he started writing his notebook. And the first chapter of the notebook is on magic squares. And you can see that section 6, there is this 4x4 Narayana Pandita's pentagonal square appearing. And then he gives an example to construct 4x4 magic squares of some 66. And both the examples are Narayana Pandita kind of magic squares, meaning constructed in the pattern with the sequences of length 8 each. Section 7 has a pentagonal square of order 8, which is constructed by the method I showed you, using 4x4, putting in 8x8. This adds up to 260. And section 8 has a general formula for a 5x5 magic square, an algebraic formula with 5 parameters. This is actually sum of 2 orthogonal Latin square kind of thing, akin to folding. Narayana's folding method for odd squares is very similar to adding orthogonal Latin squares. And he gives 2 examples. One example is the old Indian diagonal method, 1, then 2, 3, 4, 5, come down to 6, 6, 7, 8, 9, 10, then come down to 11, 11, 12, 13, 14. People who are familiar with the old diagonal method of construction of magic square. In Wikipedia, etc., it is called de la Loubre method because he popularized it in Europe. And the other one is an example of his 5x5 construction, which is a blind diagonal. So I'm saying in school, he was aware of so much advanced material, or he was so much excited about this computation of magic squares. This excitement about mathematics, I think, came very surely from the surroundings. And as Vijayaraghavan was communicated magic square by elders who were perhaps not even educated. But now Ramanujan lived in the center of Tamil culture in Kumbakonam at that time. And he would have surely learned a lot of things that were freely passing around in tradition. Now his earlier work again in notebook concerned these infinite squares. And these were used actually in 1985 to construct, calculate pi to a billion digits. These are what are called modular series. He published them in 1914, but they are written down in 1910. He published them as soon as he went to England. So in 1913, Ramanujan wrote to Hardy in a 11-page letter with over 100 results. This is just one of the 100 results that he communicated to Hardy. And the impact it had on Hardy and Littlewood was that, expressed by Russell's quote, which was read yesterday. Russell wrote to his friend Lady Morrell that he found Hardy and Littlewood in a state of wild excitement because they have discovered a second Newton, a Hindu clerk on 20 pounds a year. And then Hardy wrote back to Ramanujan saying that your results look very interesting, but I have to look at them much more carefully. But I want particularly to see your proofs of your assertions there. you will understand that in this theory, everything depends on rigorous exactitude of proof. And the same point is repeated 2 more times in the same letter. And Ramanujan wrote back to Hardy in February 27, a 10-page letter with about another 30-40 results. But here he is explaining something about his own mathematics. We should hear Ramanujan talk about his mathematics. I dilate to confuse you that you will not be able to follow my methods of proof if I indicate the lines on which I proceed in a single letter. You may ask how you can accept results based upon wrong premises. What I tell you is this: verify the results I give, and if they agree with your results got by trading on the groves in which the present-day mathematicians move, you should at least grant that there may be some truth in my fundamental basis. So this is how Ramanujan thought about his work. And he also said, I just want at this stage great mathematicians in Europe to take my results seriously. And don't misunderstood if I just give a short account. My methods are there and you will get to know them by and by. And Ramanujan goes to England, and by then he has his notebooks filled with more than 3,000 results. But having gone to England, he writes to his friend within 4 or 5 months, saying, I have changed my plan of publishing the results. I am not going to publish any of the old results in my notebook till the war is over. That is, till I return to India. I am trying to get the new results by their methods so that I can easily publish these results without delay. And he says the same thing to his another friend, Subramaniam, also. And here is a letter from Ramanujan to Ganapati Iyer, who was his friend and who had joined Presidency College as a lecturer. He is explaining that Hardy and Littlewood are wonderful mathematicians, and we had read their book Orders of Infinity earlier. They are doing research in the most difficult and advanced parts of mathematics. They have proved many properties of zeta function, which defined all attempts to prove them for these so many years. This is all being said by Ramanujan, whom people claim didn't know what a proof was. If you see the last paragraph in Matthew's theory of numbers, you will find the statement, hence we conclude that Gauss's approximation was too great. This is for the number of primes less than a number x, the function pi of x. Mr. Littlewood has proved that this is wrong beyond a certain value, a point beyond 10 to the power 10 to the power 10 to the 10. So Ramanujan knew that mere induction will not help in mathematics. That you check a result for 1 to 10 to the power 10 to the power 10, it doesn't prove it. You have to have some other argument to arrive at that result. It may fail. This is there even in Krishna Raivedya's commentary that a million instances does not prove a mathematics result. So Ramanujan wrote about 30 to 37 papers in England, 30 papers, 7 of them with Hardy. He was elected FRS in 1918. He returned to India and he wrote his last letter to Hardy on January 12, 1920, the only letter he wrote to Hardy from India, where he discusses the Mach theta functions. And he passed away on April 26th. Now, how was Ramanujan's mathematics assessed around that time? So Hardy wrote an obituary notice in 1921, and the same thing he has reproduced in his edition of collected papers. The main thing that Hardy is saying, apart from a lot of wonderful praises of Ramanujan's work, his ideas as to what constituted mathematical proof were of the most shadowy description. All his results, new or old, right or wrong, had been arrived at by a process of mingled argument, intuition, and induction, of which he was entirely unable to give any coherent account. And he also said, I can compare him only with Euler or Jacobi. In fact, they were saying Ramanujan is a great mathematician, if only he was born years ago. He worked far more than the majority of modern mathematicians by induction from numerical examples. All of his congruence properties for partitions were discovered this way. It was not, and then assessing his whole work, Hardy says, it has not the simplicity and inevitability of the very greatest work. It would be greater if it were less strange. He would probably have been a greater mathematician if he had been caught and tamed a little in his youth. Here is the review of Littlewood of the collected works of Ramanujan edited by Hardy and published in 1929. It's even more dismissive of Ramanujan. Ramanujan's great gift is a formal one. He dealt in formulae, but the great day of formulae seems to be over. He had no strict logical justification for it. This is all public domain document. obituaries and reviews printed in journals. He had no strict logical justification for his operations. He was not interested in rigor. The clear-cut idea of what is meant by a proof nowadays so familiar as to be taken for granted, almost sounding like Macaulay. He perhaps did not possess at all. If a significant piece of reasoning occurred somewhere and a total mixture of evidence and intuition gave him certainty, he looked no further. 1940, Hardy published another book based upon a set of lectures he gave in Harvard in late 30s. He says, this work of Ramanujan includes a great deal that is new, but much more that is rediscovery, and often imperfect rediscovery. And it is sometimes still impossible to distinguish between what he must have rediscovered and what he may have somehow learned. And even he goes to the extent of saying this was inevitable because he had been carrying an impossible handicap, a poor solitary Hindu pitting his brains against the accumulated wisdom of youth, the almost Churchillian comment. I should estimate that about 2/3 of Ramanujan's best work, Indian work, that is prior to coming to England, was a rediscovery. So this is how they had finished off Ramanujan by 1940. But till then, what was known about Ramanujan's work was these 37 papers. But they reprinted his two letters to Hardy, which contained about 120 results. The large corpus of his work, the one that he did before going to Europe, was in a notebook which had 3,250 results. And then what he did after coming back from England in 1 year was a sheet of papers of 100 pages, which had 600 results. And detailed analysis of this corpus began only in the last quarter of 20th century, after these notebooks were published in 57 and 88. One way, because it changed, was this great tau function, a modular function that modular form that Ramanujan considered. And he gave a conjecture, and that became very important when Peter Deligne proved this conjecture as a consequence of his proofs of Bayes' conjecture. And Deligne was given Fields Medal and later on won the Abel Prize. And around his centenary, one of the greatest number theorists of last century, Ethel Selberg, re-evaluated Ramanujan. And he says, in what has been left of all his work, including notebooks, there seems to be quite clear evidence that he had developed on his own a theory of modular forms and equations, a theory he had developed, according to Selberg. And he says that this great paper of Hardy and Ramanujan, they really did not get, they got only the asymptotic form, but they could have gotten the exact form of partition function. If only Hardy believed in what Ramanujan wrote, the result was all the way there in his letter. If only Hardy had trusted Ramanujan more, he could have gotten Rademacher formula or what even Selberg discovered. Because Littlewood and Hardy were primarily working with analysis, and they didn't know anything about, they didn't have a feeling for modular forms. And finally, he says, Louis Mardel questioned Hardy's assessment that Ramanujan was Euler and Jacobi. Mardel says one should judge a mathematician by what he has actually done, by which Mardel seems to mean the theorems he has proved. This is Selberg saying. And Selberg says, Mardel perhaps had not seen Ramanujan's notebook. I think it's a felicitous but unproved conjecture, may be of much more consequence for mathematicians than the proof of many a respectable theorem. And so this is how great mathematicians started understanding. And so other discoveries like mock theta functions are likely to be very important. This is what Selberg said. And so these notebooks of Ramanujan, Anandarao sent them to Hardy, but even Anandarao is very skeptical. He says, I fear it may look a little incongruous by the side of his mature work, meaning mature work done with Hardy in England. So anyway, I'm sending you the notebooks. People are saying it should be printed along with collected works. They did print it along with the collected works. Hardy passed on the notebooks to Wilson and Watson, and they were lying, and they were published, because once the collected papers were published and those 122 results were published, there was a clamor for publishing Ramanujan's notebook. And here is Bruce Bent explaining how his notebooks got published. Here is Bruce Bent explaining. He is writing this in the 125th anniversary of Ramanujan in 2012. He says in 1977, he started looking at notebooks, and he completed 5 volumes in slightly over 20 years. His first volume came out in 85, and the last volume, 5th volume on notebooks, came out in 19. But the most crucial thing Bruce Bent is saying, altogether, the notebooks, that is the notebooks before going to England, contain over 3,000 claims, almost all without proof. Hardy surmised that over 2/3 of these results were rediscoveries. This estimate is much too high. On the contrary, at least 2/3 of Ramanujan's claims were new at the time when he wrote them, and 2/3 more likely should be replaced by a larger fraction. More importantly, almost all the results are correct, notwithstanding the fact that no proofs were given. Perhaps no more than 5 to 10 are incorrect. Anyway, then in 1976, this last notebook, it was not found in West papers. It was found amongst Watson papers deposited in Trinity College by Andrews. And now between 2005 and 18, 5 volumes have been published, and this has been completely. It was first published in a raw form in 1987. And here Andrews and Burnt list all the topics that it contains. One of it contains is what is called this great Mach theta function. And in 2013, for the first time, the original definition of Ramanujan of Mach theta function was justified by Ono. And there is much more Ono has written. Anyway, now the main thing about Ramanujan was a doubt that was spread all around, that he didn't know proof, and he had conjecture. He had worked on induction. But Ramanujan, as I showed you from his letters, had no doubts whatsoever about his validity of its result. And he was often willing to wait and supply his proofs, if necessary, in the format it was required. But basically, he didn't want to waste his time on doing these proofs. He was all the time furiously discovering more and more interesting results. That's what Selberg says. A conjecture which is very beautiful is worth 100 times, 100 proofs are standard results. And there's a story Edward Shills is writing that Professor Littlewood was asked to teach complex variable theory to Ramanujan. But whenever Littlewood started on something, Ramanujan would go off in a tangent in his mind. He will go away and he will start with an avalanche of original ideas and discoveries. So there was no time for instructing him. Now, last 2-3 slides, Professor Sriram. The Greek constant definition of mathematics is almost equates mathematics with proof. So that the process of discovery of mathematical results can only be characterized vaguely as intuition, natural genius, etc. And it also believes mathematical truths are non-empirical, so they can be obtained only by pure logical reason. Of course, there are critics of this philosophy of mathematics. Now, even Hardy, of course, believed this to the core. He thought that only Greeks did mathematics, and only mathematical results are permanent. And he thought that immortality may be a silly word, but probably mathematician has the best chance of whatever it may mean, that mathematical truths are eternal truths. In the Indian mathematical tradition, as known from all the texts in the last 2 to 3 millennia, mathematics was not equated with proof. Ganita was computation. Upapatti proof was a part of mathematics. Mathematical results were not perceived as non-empirical. They could be validated in diverse ways. But the need for validation, they always knew, was very important. And acceptance of a result by a community of mathematicians was more important than proving it to be absolutely true forever. So instead of the joke that Bertrand Russell had with his lady friend, Narayan and Ramanujan need not be compared to a Newton, but actually, if he is to be compared, it was not that he was Nabhuto, because there is Madhava, there is Bhaskara, there is Aryabhata, there is Brahmagupta. So he has to be compared with the greats of Indian mathematics. And in terms of his felicity in handling iterations, infinite series, continued fractions, and transformations of them, he was much more than Jacobi. He was somebody like Madhava, the founder of the Kerala school. And for Nabhavishyati, if we don't study his work, and if we don't analyze his work, if we don't try and understand his work, of course, we may lose the native Indian genius that Ramanujan was a representative of in the 20th century. I thank the organizers for giving me an opportunity to speak on Ramanujan with my very limited knowledge on this occasion. Thank you very much.
Thanks a lot, Professor MD Srinivas. It's a very good talk, though it was very short. I just want to make 1 or 2 comments. I'm sorry there will be no questions. See, I think Professor Srinivas made very, very important, some points, in his talk. So the thing is, we get carried away by some assessments some Western scholars made about 40 years back, 50 years back, which, they would have done with some very limited amount of data or limited amount of understanding. So that is happening not only in history of mathematics, but in all spheres of Indian life. We get carried away when somebody, some Western person, praises us, or we just, become crestfallen if somebody denounces us. Arey Baba. So it is very important that we should have our own assessment. That's the important thing. I mean, it need not be always adulatory. I mean, you need not be praising everything. I mean, we need not glorify everything. But we should definitely have our own assessment, and also the assessment of others also are important, but we should go into their assessment. You see what they are seeing, what do they know, what is their database, on what database they are making their conclusions. So these things are very important. So anyway, I don't have to go through all that again. So now I hand over this thing to Dr. Darshana Prajapati will make a brief summary of the conference. Over to Dr. Darshana.
Thank you, sir. Professor M.S. Sriram, President of Indian Society of History of Mathematics, Professor S.G. Dani, DAE Center for Basic Sciences, Mumbai, Professor K. Ramasubramanian, Academic Secretary of Indian Society for History of Mathematics, Professor R.C. Gupta, Jhansi, and founding member of Indian Society for History of Mathematics and past editor of Ganit Bharti, Professor Mahesh Joshi, Admin Secretary of Indian Society of History of Mathematics, and other dignitaries present in the conference. I, Dr. Darshana Prajapati, welcome you all on behalf of organizing committee and Indian Society for History of Mathematics in the valedictory function of International Web Conference on History of Mathematics organized by Indian Society for History of Mathematics, Delhi. It feels honored to present a report of 3-day international conference organized during December 20 to 22, 2020. This conference received a large number of participants from across the globe. Total more than 43 abstracts were received and 30 talks were delivered by renowned professors, mathematicians, and researchers from different parts of the world, covering all aspects of history and development of mathematics. The conference was inaugurated by Professor R.C. Gupta on 20 December 2020 at 10 a.m. In his address, Professor Gupta recalled his long association with Indian Society for History of Mathematics and Ganit Bharti. He emphasized the need for the younger scholars of history of mathematics in India to study all sources, materials, situations, and develop the ability to study the material in Sanskrit and other languages too. He also emphasized the need for having courses on Indian mathematics at PG level. Professor M.S. Sriram delivered welcome speech and also gave the overview of the conference. He addressed the need for Indians to have their own assessment of the Indian tradition in mathematics and other traditions too. Professor M.C. Joshi gave a vote of thanks at the end of the inaugural function. Session 1 was scheduled during 10:30 a.m. to 1:15 p.m. on 20 December 2020. Professor S.G. Dani chaired the session, in which Professor M.S. Sriram, K.V. Sharma, Research Foundation Chennai, spoke about some not well-known calculus idea in the Kerala School of Astronomy and Mathematics. Professor Venkateswara Pai, IZ Pune, Professor Aditya Kolachana, IIT Madras, Professor K. Mahesh, IIT Bombay, Professor K. Ramasubramanian and D.G. Suryanarayan, IIT Bombay, discussed on various topics related to the history of mathematics.
Hello, Amartya. I'm Amartya. Can somehow this announcement be made that Manjul Bhargav is talking on Ramanujan today at 7:30 p.m.? That may be very valuable.
On 20th December 2020, which was chaired by Professor M. Sriram and Tarun Kumar Das, University of Delhi. In this session, Professor Satyam Kichenasamy from France discussed on the impact of history on modern research and teaching. Professor Nicolo from Italy, Professor Agathe Keller from Paris, Professor Jens Heuroff from Denmark, Syed Said Aga Beni Hazami, IH University from Iran, Ekaratna Acharya and Krishna Prasad Bhatta, Tribhuvan University, Nepal, also presented papers on the various aspects of history of mathematics. On December 21st, 2020, during session 1, during session 3 was chaired by Professor Anupam Jain, Kunda Kunda Gyanapita Indore. In this session, Professor Amriti Kumar Datta, Indian Statistical Institute, Kolkata, talked on arithmetic mean in ancient India and Europe. Professor S.G. Dani, Professor Ram Kalyani, Venkat Raman, Professor K.V. Sharma Research Foundation, Chennai, Professor Sita Sundar Ram, Professor Gopinath from Indian Institute of Science, Bengaluru, Professor Omkarla Srivastav and Professor Sumita Srivastav from Rajnandgaon, Professor G.S. Rawat and Professor Mahesh Joshi from Kumaon University, Nainital, threw light on ancient Indian mathematics and work of Indian mathematicians. Session 4 was chaired by Professor Mahesh Joshi and Dr. Darshana Prajapati. In this session, Professor S.A. Katre from Savitribai Phule University, Pune, delivered a talk on names of decimal places in Sanskrit language. Professor Anupam Jain from Kunda Kunda Gyanapita, Indore, discussed on Lilavati, Ek Lokpriya Naam. Dr. Deepak Jadhav and Dr. Shainik Bandi, Professor Avinash Sathaye and Dr. Amita Joshi talked on contribution of Bhaskaracharya, Brahmagupta and related aspects, and also Ramanujan in the field of mathematics. During 5 to 6:30 p.m., a technical session was organized, which was chaired by Professor Omkarla Srivastav and Professor M.C. Joshi, wherein around 15 researchers presented their work. On 20th date, Indian mathematician Srinivas Ramanujan. On this auspicious day, Session 5 was organized under the chairmanship of Professor K. Ramasubramanian during 10 to 12:30 p.m. Professor Jonathan from Australia delivered a talk on Brahmagupta's definition of Sunya failing to be transmitted to Renaissance Europe via the Arabic world. Dr. Udayraj Patare from Ahmednagar talked on a model-based analysis of COVID-19, big data, and advanced linear algebraic approach. Professor Keshav Melnath, IIT Gandhinagar, Professor KVVNS, Sundari Kameshwari from Ghaziabad talked on various topics related to history of mathematics. Professor M.D. Srinivas from Center for Policy Studies, Chennai, gave a detailed exposition of the folding method of Narayan Bandita in the construction of magic squares. He has given a brief talk on the life and work of Srinivas Ramanujan in the valedictory session. After the fruitful deliberations during the 3-day web conference, we hope that all are benefited in one way or other. So this was the brief report of the 3-day conference. I thank you all on behalf of organizing committee, Indian Society for History of Mathematics, and my personal behalf. Thank you all.
Thank you, Dr. Darshana. Thank you for a very apt summary. So now I will call upon Professor Anupam Jain to deliver the vote of thanks. But after the vote of thanks, so there are a few announcements, for instance, Professor Amartya Datta wants to bring to our notice a lecture by Manjul Bhargava. So after vote of thanks, don't leave. Okay? Okay. Professor Anupam Jain, please.
Respected Chairperson, Professor M.S. Sriram, and dear participants. I consider this conference is remarkable and very successful due to wide participation of the scholars from various countries and different parts of our country. This is my humble note to acquaint you with our feelings and sentiments. that the organization of this international web conference on history of mathematics was a big task for our society. I am very much thankful to our president, Professor M.S. Sriram, for taking initiative and providing active and effective leadership. I am also thankful to renowned scholar Professor R.C. Gupta, who is the founder member of Indian Society for History of Mathematics, for his inaugural address and creative suggestions to the society as well as for participants. My sincere thanks to our past president and editor Ganit Bharti, Professor S.G. Dani, and eminent speakers of the foreign universities. I am also thankful to Professor Ram Subramaniam, Professor Mahesh Joshi, Professor Tarun Das, Professor Darshana Prajapati, Dr. Virendra Dalal, and their team members for taking technical issues and their organizational work. I also thank to my colleagues of organizing and program committee. I am thankful to all the participants who presented their papers and delivered invited talks on various subjects. I hope we will soon come out from this pandemic situation and we will meet in next conference of Indian Society for History of Mathematics in person. Best wishes to all of you for the good health in 2021 and congratulations for National Mathematics Day. Thank you to all of you.
Thank you, Professor Anupam Jain. It is a very, very good these things. He included all the persons who made it this web conference a success. Of course, we are a little apprehensive, because this is the first time. In fact, it's the first time for many people, not only for organizing but for talking also. But I think it went on very well, so it's very good. So before signing off, I think Professor Amartya Datta, can you please make an announcement? Yeah.
Yes, just as continuation of Professor M.D. Srinivas and your remarks about Ramanujan, today at 7:30 p.m. there will be a talk by Manjul Bhargav on mathematical genius Srinivas Ramanujan. This is under Vigyan Prasar, a part of Ramanujan Yatra. So I think you can locate it. I think you just go to the Vigyan Prasar, Vigyan Prasar, and you go to their website, you will be able to locate it, or you, if you have a problem, you write me an email, then I'll just forward this announcement. Many of you. So please listen to this. As Sriram said that we should listen to our own assessment of Ramanujan, and who better can do it than Manjul Bhargav, who is a number theorist himself. Yeah, that's 7:30 p.m.
No, you have to unmute yourself, Sriram.
Yeah, sorry. So very good. I think now we can call it a day. It went on very well. I think all these talks and also the comments, and it's very nice. Okay, so we'll sign off now. I think people can
Yeah,
Ram Subramaniam, yes.
No, see, I just want to mention that Professor Sriram took enormous efforts in making this happen. So we thank the president of ISHM for having taken so much of interest in conducting this conference. So it was a great success. Thank you so much.
I should thank Ram Subramaniam for making this link possible. You see, otherwise it would have been in a soup. Yeah, at short notice he made it available. Yeah.
I want to announce one thing, sir, with the permission of Sriram, sir.
Yeah.
This is a good conference, and we wish that we must have a good memory of all the participants. So we all make our video on so that we can take group photographs. I will take a group photograph of all the participants. All the participants are requested to keep their video on.
Yeah, okay. So please unmute your videos.
Unmute your videos.
It's a good idea. In fact, this is a very special conference in which Professor R.C. Gupta could also participate. So
yeah, that's good. Yeah.
we thank his son-in-law. So he is just smiling in front of us. I'm so delighted. So that this could happen. Yeah.
Yes, group photograph will be on. Yeah.
Darshana, is it okay?
Just a minute.
All the.
Just a minute, sir.
Yeah, yeah, please.
Yeah,
Just
that's
a
all.
minute,
Very
just a
good.
minute, sir. Yeah, yeah.
A good gallery.
I'm checking. Keep your video on. I am not able to see some of the participants. Just a minute, sir. Okay. Good, 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 good. Only few minutes now, because total 38 participants are there, and okay, okay. Now, thank you all. Now we can leave the meeting. Thank you, sir.
Okay. Thank you.
Thank you.
Thank you. Good.
Thank you very much. Thank you so much.
Thank you. Yeah.
Okay. Bye-bye.
Okay.
Thank you.